Nevada is home to some of the biggest construction projects in America right now. From billion-dollar developments rising out of the desert to game-changing infrastructure on a massive scale, these megaprojects are transforming the state like never before. In this video, we reveal the 10 biggest construction projects ever built across Nevada. Rising from the arid landscape of Story County, Nevada, the Gigafactory Nevada was conceived as a cornerstone of Tesla's ambition to revolutionize battery production at an unprecedented scale. Construction began with extensive earthworks to level the undulating terrain. The site, chosen for its proximity to rail lines and major highways, required vast quantities of excavation and grading. Bulldozers and graders reshaped the desert floor, while stormwater management systems were installed to direct runoff during rare but intense rainfall events. Once the pad was prepared, engineers focused on laying the foundation. Due to the immense footprint, eventually designed to exceed over 13 million square feet, the slab had to be poured in meticulously scheduled phases. Reinforced concrete was poured in segmented pours, each with embedded conduits and anchor bolts for future equipment. The structural frame was composed of prefabricated steel columns and trusses, delivered in sequenced shipments and lifted into place with crawler cranes. Crews worked in rotating shifts to maintain continuous progress, erecting hundreds of structural bays in parallel operations. Inside, the factory's layout followed a vertically integrated production flow. Raw materials entered at one end and passed through successive stages of battery cell fabrication, module assembly, and finally powertrain integration. To support this, the building's design included wide-span bays and a column-free floor plan for maximum flexibility. Utility corridors were embedded both overhead and beneath the slab to house compressed air, process water, chilled water lines, and high-voltage electrical conduits. HVAC systems were configured to manage precise temperature and humidity tolerances essential for lithium-ion battery production. In terms of energy use, the building was engineered to eventually operate on renewable sources. Roofing was structured to support photovoltaic panels, and internal systems were optimized for energy recovery and minimal waste. Fire suppression posed unique challenges due to the chemical nature of the materials. Thus, specialized foam systems and compartmentalized fire zones were integrated into the design. Construction logistics had to accommodate a remote site with limited access roads. Materials were staged off-site and trucked in with just-in-time precision to minimize storage on the congested site. Labor coordination was also a challenge, requiring thousands of workers from multiple trades and subcontractors, all operating under tight schedules and strict safety protocols. By scaling battery production to such a degree, Gigafactory Nevada marked a shift in how energy storage systems could be manufactured, economically, locally, and with the intent of creating a closed-loop supply chain. At the outset of the MSG Sphere's construction in Las Vegas, the most immediate challenge was establishing a foundation capable of supporting a structure unlike anything previously built. The sphere's extreme diameter, spanning over 500 feet, and height exceeding 300 feet, necessitated a ring of deep foundation caissons. These caissons, drilled dozens of feet into the caliche-laden desert subsoil, provided load-bearing support for the concrete mat foundation that would carry the entire dome. Crews installed dense rebar cages and tremie-poured concrete in segments, ensuring continuous integrity under the enormous compressive and lateral loads. The frame of the sphere was formed using a hybrid structural system combining concrete cores with an extensive steel diagrid shell. The steel members, many of them curved and custom fabricated, were craned into place with extreme precision. Each joint had to accommodate subtle geometric variances in the spherical curvature, requiring extensive use of laser surveying and point cloud modeling during assembly. The use of node connectors, each one custom engineered, allowed thousands of steel segments to interlock into a stable geodesic structure. Work progressed concentrically, rising from the base upwards, forming a self-supporting lattice that grew in stages toward closure at the apex. Internally, the complexity intensified. The sphere's defining feature, its fully immersive LED display surface, required a compound curved interior supported by catwalks and rigging systems hidden behind the paneling. This interior surface included more than 100,000 square feet of high-resolution LED panels. Engineers had to account for thermal expansion, cable routing, and precise angles of incidence for projection mapping and acoustics. To achieve truly immersive sound, an advanced beam-forming audio system was suspended behind acoustic mesh panels, calibrated to direct audio precisely to each seat using an array of over 100,000 speakers and transducers. Externally, the sphere's envelope was sheathed in an exoskeleton clad with LED modules designed for all-weather performance. These panels were mounted using modular aluminum frames anchored directly to the diagrid steel. Wind loading, thermal cycling, and desert dust all influenced the choice of materials and mounting systems. Throughout the build, access was achieved with a mix of suspended scaffolds, articulating lifts, and perimeter ring cranes. Construction sequencing had to account for limited laydown space and active coordination with surrounding infrastructure. With the Las Vegas Strip nearby, noise restrictions, traffic control, and night work all shaped how the project advanced. The MSG Sphere stands as a demonstration of digital architecture converging with structural audacity, where immersive entertainment dictated the blueprint from foundation to facade. Shifting focus to one of the most significant sports construction projects in recent American history, Allegiant Stadium in Las Vegas began with an enormous excavation effort to prepare the site just west of the Strip. The soil conditions required pre-treatment due to high water tables and loose granular fill. To stabilize the subgrade, contractors used deep soil mixing and installed wick drains to accelerate consolidation. Once the pad was secured, work commenced on the foundation, which incorporated hundreds of drilled piers and massive concrete footings to support the superstructure. The building's primary frame featured a combination of steel trusses and precast concrete components. One of the defining features of the stadium, the sweeping roof canopy, was enabled by a network of long-span steel trusses, each weighing several hundred tons. These elements were fabricated off-site and delivered in sequential shipments, where they were assembled using gantry cranes and specialized rigging equipment. The roof itself was a cable-supported ETFE system that demanded meticulous tensioning and anchorage precision to accommodate thermal movement and wind uplift. Inside, the seating bowl was configured with precast raker beams and vomitory walls, each piece carefully aligned to maintain sightlines and support tiered loads. The lower bowl was cast in place, while the upper levels were constructed using a combination of steel risers and precast planks. Mechanical systems were housed in interstitial levels between the concourses and integrated into the structure to reduce noise and vibration transmission. One particularly ambitious component of the project was the operable field tray. Designed to support natural grass for NFL games, the tray rested on a series of rails embedded in the foundation slab. It could be rolled in and out of the stadium using hydraulic motors and steel wheel assemblies, weighing several million pounds in total. This required structural coordination with the surrounding apron and subgrade drainage systems, which had to accommodate both static and dynamic loads without settlement. Facade construction involved a high-performance curtain wall system clad in black fritted glass and metal panels. Behind this outer skin, wind bracing and thermal barriers were integrated to manage the desert climate. Each section of the envelope was panelized off-site and installed via mobile cranes in a rapid sequence, closing in the building in time for interior finishes to commence. Allegiant Stadium represents a convergence of speed, scale, and innovation completed on a fast-track schedule that demanded round-the-clock coordination across hundreds of trade contractors. In the vast and rugged terrain of western Nevada, the Greenlink West Transmission Line project began with a series of extensive environmental and geotechnical surveys. This corridor, stretching hundreds of miles, demanded careful route selection to avoid sensitive habitats, archaeological sites, and unstable soil zones. Once the alignment was finalized, crews mobilized with access road grading as the first priority. In remote desert areas, temporary haul roads and helicopter pads were established to enable movement of personnel, equipment, and materials to tower sites that had no existing access. Tower foundations varied depending on soil conditions. In rocky upland zones, foundation crews used blast hole drilling, followed by concrete anchors set deep into fractured bedrock. In softer or sandy valley floors, deep bored shaft foundations were poured with reinforced concrete, sometimes with steel casing to prevent wall collapse. Each foundation was designed to handle both axial and lateral loads imposed by conductor tension and wind shear on the towers. Concrete had to be batched locally or transported in rotating mixers across significant distances, requiring careful coordination to ensure consistency and curing integrity. The transmission towers themselves were largely lattice steel structures, fabricated off-site and delivered in sectional bundles. Erection crews used tracked cranes where terrain allowed, while in the steepest sections, helicopters were employed to lift tower segments into place. Ground crews then bolted the segments together using high-strength structural fasteners. Each tower was surveyed post-erection for verticality and alignment, using laser theodolites before conductor stringing began. Conductor installation involved multiple phases. First, pilot lines were pulled between towers using drones or helicopters. These were then used to draw in heavier steel messenger cables, which in turn pulled in the high-voltage conductor bundles. Each conductor was tensioned using hydraulic pullers and tensioners to exact sag tolerances specified in the design documents. Spacer dampers were installed at calculated intervals to prevent aeolian vibration, and insulators, often made from composite polymer materials, were mounted to separate the live conductors from the grounded towers. Substations on either end of the line required massive transformers, circuit breakers, and control systems to manage voltage conversion and grid integration. These substations were built concurrently, with site grading, pad installation, and bus work assembly proceeding, while the main line was being erected. The Greenlink West project not only involved transmission infrastructure, but also included communications fiber installation and SCADA integration for remote monitoring, forming a backbone for a more resilient and renewable-focused power grid across the region. Where a coal-fired power plant once dominated the landscape in Moapa, Nevada, the construction of the Reed-Gardner battery storage system marked a shift toward clean energy storage and grid stabilization. The first phase of the project began with demolition and site remediation. Existing utility corridors, concrete pads, and buried infrastructure from the retired power plant had to be removed or repurposed. Soil testing and grading ensured that the land met the geotechnical requirements for placing a large array of battery enclosures and associated electrical equipment. Once the site was prepared, the foundation work proceeded with a modular strategy. Each battery container, typically the size of a shipping container, rested on reinforced concrete pads designed to bear static loads while allowing thermal expansion. These pads were poured with integrated cable trenches and embedded conduits for power and control wiring. The layout followed a linear alignment to optimize airflow, simplify maintenance access, and facilitate short routing to the power conversion systems. The energy storage units themselves consisted of lithium-ion battery cells housed in steel containers with integrated fire suppression, HVAC, and thermal monitoring systems. These containers arrived pre-assembled and were offloaded using mobile cranes or forklifts, then anchored in place with structural hold-downs. Adjacent to each group of battery containers, power conversion systems were installed, which included bidirectional inverters, transformers, and medium-voltage switchgear. These systems allowed the batteries to interface with the regional grid, converting stored DC energy into AC power during peak demand periods and drawing excess electricity during off-peak times. Cable terminations and system integration required detailed coordination. High-voltage AC and low-voltage control wiring were routed through separate underground duct banks to minimize interference. Grounding grids were installed beneath the entire array, bonded to each enclosure and system cabinet to ensure personnel safety and lightning protection. The site also included perimeter fencing, surveillance, and access control in compliance with NERC reliability and cybersecurity standards. A supervisory control and data acquisition system tied all battery enclosures, inverters, and transformers into a centralized control hub. Fiber optic links and programmable logic controllers enabled real-time monitoring of temperature, voltage, current flow, and system health. In addition to the core storage function, the installation featured black start capabilities and reactive power support to bolster grid stability during contingency events. Unlike many arenas that rise from open space, the T-Mobile Arena in Las Vegas was constructed on a tightly constrained urban site, requiring deep logistical planning before the first shovel hit the ground. The initial site preparation involved extensive utility relocation, as existing storm drains, water lines, and power conduits had to be rerouted to accommodate the building footprint and its supporting infrastructure. With minimal laydown space available, construction sequencing was planned in detail to ensure materials arrived just in time for installation. The structural system relied on a hybrid steel and concrete frame. A reinforced concrete core formed the arena's vertical circulation spine and housed elevator shafts, stairwells, and mechanical risers. Around this core, a complex array of steel columns, raker beams, and trusses supported the sweeping roof and cantilevered seating decks. The roof was particularly challenging, as it required long-span trusses to bridge the open interior without intermediate columns, allowing unobstructed views from all seats. These trusses were lifted into place using synchronized crane lifts and were temporarily braced until lateral systems were completed. Within the bowl, precast concrete seating components were craned into position and set atop steel support members. The lower bowl was poured in place using cast-in-place concrete, allowing for integration of conduit chases and drainage systems directly into the slab. To ensure optimal acoustics, the interior envelope was lined with a combination of perforated metal panels and acoustic baffles, carefully arranged to diffuse sound energy and minimize echo. Mechanical systems were installed using vertical and horizontal distribution zones to maximize ceiling clearance and fan comfort. Chilled water plants, air handling units, and ductwork were located primarily above the event floor and distributed outward through high-level plenums. Special attention was given to integrating smoke control zones, emergency exhaust fans, and CO2 sensors into the overall HVAC design. Electrical systems featured redundant feeds, backup generators, and an extensive network of lighting control nodes to accommodate both performance and broadcast demands. The arena's exterior featured a curved facade made up of glass curtain wall, aluminum panels, and exposed structural elements. These were installed in phased sequences, using mast climbers and boom lifts to operate within the spatial limits of the surrounding development. Water infiltration protection was handled using rain screen design and perimeter sealant systems, ensuring long-term envelope integrity in the arid climate. Construction of the Brightline West high-speed rail begins not with rails, but with an extensive corridor preparation effort stretching along the Interstate 15 right-of-way between Southern California and Las Vegas. The alignment was selected to leverage existing transportation corridors, minimizing environmental impact while reducing the need for new land acquisition. Survey teams marked out the route using GPS-based geolocation, after which clearing and grubbing crews removed desert vegetation and leveled the alignment in preparation for subgrade construction. Due to varying soil conditions, crews implemented soil stabilization techniques such as cement treatment and moisture conditioning to achieve the compaction required for long-term settlement resistance. The rail substructure comprises several layers, beginning with compacted subgrade, followed by engineered fill, and a layer of ballast in zones where traditional track is used. However, in high-speed segments, especially those reaching over 180 miles per hour, a concrete slab track system will be utilized. This involves pouring continuous reinforced concrete slabs with expansion joints and embedded fasteners designed to hold the rail in place with millimeter-level precision. These slabs are set atop geotextile membranes and drainage systems to prevent water infiltration and thermal heave. Bridges and viaducts form a critical part of the project, particularly where the line crosses over existing roadways or environmentally sensitive terrain. Precast concrete girders are transported via specialized haulers and lifted using high-capacity gantry cranes. Abutments and piers are constructed using drilled shaft foundations, with rebar cages tied on site and lowered into the shafts before concrete placement. In seismic zones, isolators and energy-dissipating devices are installed to ensure structural resilience during earthquake events. Catenary systems for electric power delivery require the installation of overhead contact system, poles spaced at precise intervals along the corridor. These poles are anchored in concrete footings and support tensioned copper conductors delivering 25 kilovolts AC. Power substations are built at strategic intervals, converting utility-scale electricity to the necessary specifications for the trains and feeding the system through switchgear and protection circuits. Stations are designed as intermodal hubs, integrating ticketing systems, security screening, vertical circulation, and baggage handling. Platform edge doors, vibration-damping structural slabs, and acoustically treated canopies are incorporated to ensure comfort and safety at high-speed boarding conditions. All systems are tied into a centralized traffic control center that uses fiber optic networks and redundant data links for command, monitoring, and dispatch. Brightline West aims to redefine regional travel by delivering a fully electric, high-capacity corridor built with exacting civil and systems integration standards tailored for American infrastructure. Breaking ground on the new Las Vegas Stadium project involves an immediate confrontation with both scale and site complexity. Before construction on any vertical elements could begin, civil crews undertook mass grading operations across a site encompassing dozens of acres situated near critical transport infrastructure. Excavation equipment worked around the clock to balance cut and fill volumes, and sediment control basins were installed to comply with regional stormwater regulations. Soil stabilization techniques, including lime treatment and compaction grouting, were applied in zones identified by geotechnical surveys as having potential for settlement. The structural skeleton of the stadium is expected to be a composite of reinforced concrete cores and structural steel framing, optimized to support a multi-tiered seating bowl and a retractable roof or canopy. Temporary shoring towers and formwork systems will be deployed to construct the poured-in-place vertical cores, which will house elevator banks, mechanical risers, and egress stairs. Once the cores reach adequate height, sequential steel erection will begin. This involves the staged installation of primary steel columns, roof trusses, and raker beams, using crawler cranes capable of operating at tight radii due to the constrained urban site. Simultaneously, the substructure below grade will include utility tunnels, equipment vaults, and mechanical rooms. These require waterproofing membranes, concrete admixtures for sulfate resistance, and cast-in-place slab systems with embedded sleeves for mechanical and electrical penetrations. Mechanical engineers will be installing a central chilled water plant, routing large-diameter piping through below-grade trenches and into elevated concourses through a system of vertical shafts and distribution headers. The stadium's envelope will likely employ high-performance glazing, custom aluminum rain screen panels, and photovoltaic-ready roof surfaces. These components will be supported by secondary steel framing and sealed using multiple air and moisture barrier systems. Installation of the facade will proceed from multiple elevations concurrently, using mast climbers and suspended scaffold systems. Wind bracing and lateral load transfer connections will be closely monitored during this phase using field weld inspections and survey control points. Interior fit-out will be driven by overlapping trades working in tiered zones, beginning in back-of-house service corridors and proceeding outward to premium suites, concessions, and seating areas. Audio-visual integration, including massive LED boards, arena-grade speaker systems, and real-time data infrastructure, will require extensive cable tray systems and climate-controlled control rooms. The new Las Vegas Stadium will ultimately stand as a hyper-engineered fusion of sports architecture and logistical orchestration, delivering a landmark capable of hosting international events and enhancing the city's already iconic skyline. One of the most logistically demanding elements of the Las Vegas Convention Center expansion was its integration with an active facility that could not afford operational downtime. The construction team had to carefully phase demolition, excavation, and vertical build-out around major events and conventions, often working night shifts and off hours to avoid disruptions. The expansion project added more than 1 million square feet of new space, including exhibit halls, meeting rooms, and circulation areas, requiring a steel and concrete structural system capable of spanning large, column-free zones. The foundation work began with deep excavation and pile driving. Given the loose alluvial soils common in the Las Vegas Valley, crews installed hundreds of auger-cast piles, each reinforced with steel cages and Tremie-poured concrete. A thick mat slab was then poured over this foundation grid, embedded with conduits for electrical distribution and floor drainage systems. The use of high-strength concrete mixes with specific slump tolerances ensured uniform performance and reduced cracking across the massive floor plate. The superstructure utilized a composite framing system combining wide-flange steel beams and concrete floor decks cast over metal decking. This method provided both strength and speed, allowing trades to follow closely behind the steel erection teams. Tower cranes and mobile telescopic cranes hoisted beam segments and roof trusses into place. For the convention hall roofs, long-span trusses were assembled in staging yards and lifted in modular sections to minimize on-site welding and alignment complexity. Mechanical, electrical, and plumbing systems were designed with scalability and adaptability in mind. Overhead utility zones carried air handling units, fire suppression mains, and lighting circuits along open web joists. These zones were isolated for sound attenuation, using acoustic baffles and vibration isolators to prevent mechanical noise from disrupting presentations and exhibits. Air distribution was handled through a combination of high-volume diffusers and underfloor displacement systems, ensuring comfort across densely populated exhibit spaces. The facade was clad in curtain wall glazing, aluminum composite panels, and architectural fins designed to reduce solar heat gain while delivering a visually striking presence along the strip. Exterior systems were tested for wind and water penetration using mock-up assemblies before full-scale deployment. The entire expansion was tied into a building automation system, enabling real-time monitoring of energy use, HVAC status, and life safety systems across both new and existing facilities. Perched high above the Colorado River, the construction of the Mike O'Callahan-Pat Tillman Memorial Bridge required a level of structural precision and environmental coordination seldom encountered in highway infrastructure projects. Spanning nearly 900 feet across the Black Canyon, just downstream of the Hoover Dam, the project's location presented formidable challenges, including extreme elevation, rugged topography, high winds, and protected surroundings. The goal was to reroute U.S. Route 93 traffic off the Hoover Dam, necessitating a bypass bridge that could support heavy truckloads while enduring significant thermal and seismic forces. Foundation work began with the construction of vertical columns anchored into the canyon walls. These columns required deep rock sockets drilled into the solid bedrock on both the Nevada and Arizona sides. Blasting, rock bolting, and controlled excavation were used to establish working platforms and construct reinforced concrete footings. Once the columns were complete, temporary cable stays were strung across the canyon to support the next phase, the twin-rib concrete arch that would ultimately carry the bridge deck. This twin arch was built using a cantilever segmental method. Crews cast concrete segments outward from each canyon wall in balanced pairs, inching their way across the gap with the aid of a cable-supported highline system and traveling formwork. As each segment cured, post-tensioning tendons were tensioned internally to bind the structure and prevent shear or flexural failure. Each section was surveyed and adjusted using hydraulic jacks to maintain precise alignment as the arch legs advanced toward mid-span. Upon closure of the arch, deck construction commenced. Steel girders were lifted by cranes stationed on temporary towers and connected to the arch ribs through vertical spandrel columns. The bridge deck itself was a cast-in-place concrete slab, poured in sections with embedded rebar and expansion joints to accommodate thermal movement. Barrier rails, lighting systems, and crash protection were then installed along the deck edges. Wind and seismic design were paramount. The bridge incorporates tuned mass dampers and elastomeric bearings at key support points, allowing it to flex under dynamic loading without structural compromise. To ensure safety during construction, catwalks and harness points were anchored throughout the span, and workers operated under a highly regimented fall protection protocol. Stretching across the coastal plains of Kennedy County, Texas, the Penascal Wind Power Project showcases the application of large-scale renewable energy infrastructure in a challenging environment defined by soft soils, high humidity, and persistent coastal winds. The construction process begins with extensive site development, including topographical surveys, environmental assessments, and access road construction through otherwise undeveloped ranch land. These gravel roads must support the transport of extremely long turbine blades, tower sections, and nacelles, necessitating careful grading, compacted subbases, and wide turning radii for specialized transport vehicles. One of the primary engineering tasks in this project involves the foundation work for each wind turbine. The coastal soil profile, composed largely of silts and clays with varying moisture content, demands a foundation solution capable of resisting both vertical dead loads and dynamic overturning forces induced by wind. Each turbine foundation typically consists of a large circular reinforced concrete pad, often exceeding 50 feet in diameter and several feet thick, with a central pedestal rising above grade. The foundation is constructed after excavation, followed by rebar cage placement, anchor bolt installation, and a continuous concrete pour to ensure uniform curing and structural integrity. The turbine towers are delivered in multiple tubular steel sections, which are bolted together on site using tensioned bolts and high-strength flanges. Erection is carried out using hydraulic or lattice boom cranes with lift capacities tailored to the height and mass of each tower segment. Each tower supports a nacelle, a housing unit for the generator, gearbox, and control electronics, which is lifted and mounted at heights reaching over 200 feet. Rotor assembly involves attaching 3 fiberglass reinforced blades to a central hub on the ground, then lifting the entire rotor assembly as a single unit and mating it with the nacelle. Electrical infrastructure includes the installation of underground medium voltage collection lines connecting each turbine to an on-site substation. These cables are buried in trenches with warning tape and sand bedding to prevent damage and ensure thermal dissipation. The substation steps up the voltage from around 34.5 kilovolts to transmission levels, often around 138 kilovolts, for integration into the regional grid. Control buildings house switchgear, protection relays, and SCADA systems that allow for remote monitoring and turbine control. Given the site's proximity to the Gulf of Mexico, the project incorporates several measures for corrosion resistance, including galvanization of structural steel, marine-grade coatings on exposed equipment, and sealed electrical enclosures. Turbines are fitted with lightning protection systems that channel electrical discharge safely to ground, a critical feature in a region prone to frequent thunderstorms. Operational testing involves synchronization of the turbines to the grid, blade pitch calibration, yaw system checks, and vibration analysis to ensure balanced rotation. Once commissioned, the Penascal Wind Power Project contributes hundreds of megawatts of clean energy, capitalizing on the consistent wind resources of the South Texas coastline, while demonstrating advanced construction sequencing and logistical planning in renewable energy deployment. Breaking ground on what is envisioned to become the largest retail and entertainment complex in North America, American Dream Miami is a mega project that combines commercial ambition with vast construction scale. The site, spanning several hundred acres in northwest Miami-Dade County, required extensive groundwork before vertical construction could even be considered. Initial site development involved substantial clearing and grubbing of existing vegetation, followed by the removal of unsuitable soils and replacement with engineered fill. Soil compaction and moisture conditioning were conducted systematically, zone by zone, to meet strict geotechnical specifications given the project's susceptibility to high water tables and the underlying karst limestone. Stormwater management was one of the most critical challenges from the onset. Crews installed a comprehensive drainage network composed of perforated HDPE pipes, catch basins, and retention ponds to control runoff during South Florida's intense rainfall events. Because of the site's proximity to sensitive wetlands, strict environmental controls had to be maintained throughout construction. Silt fences, turbidity barriers, and regular environmental monitoring were deployed to ensure compliance with state and federal mandates. The primary structure of the complex comprises a combination of reinforced concrete and structural steel, chosen based on load distribution needs and span requirements. While concrete forms the foundation mat and shear walls, wide-span areas such as the indoor ski slope, water park enclosure, and retail atriums utilize steel framing with long-span trusses and moment connections. The ski slope, one of the central engineering feats, requires a climate-controlled interior envelope over several hundred feet long, with complex thermal insulation and vapor barrier systems. The structural shell is thermally isolated from the surrounding environment, using insulated metal panels and a controlled HVAC system designed to maintain sub-freezing temperatures in a tropical climate. Mechanical, electrical, and plumbing coordination was a substantial portion of the build process, with extensive BIM modeling used to resolve spatial conflicts in densely packed service corridors. Chilled water systems, electrical bus ducts, and fire sprinkler mains all had to be routed through the superstructure without interfering with visitor circulation, escalator shafts, or themed architecture. Substations and cooling towers were strategically located in peripheral service yards to reduce ambient noise and heat near visitor zones. Specialized foundations were needed in areas designated for amusement rides, where dynamic loads exceeded standard building tolerances. Engineers embedded deep auger cast piles beneath the footings to transfer those loads to stable substrata. Vibration isolation systems and seismic expansion joints were installed at strategic intervals to ensure ride safety and structural resilience. Exterior construction involved a layered system of weather-resistant barriers, rain screen cladding, and themed facades that change appearance depending on the function of each zone. Materials ranged from precast concrete panels to architectural glass and high-pressure laminates. For the water park roof, translucent ETFE panels were chosen to allow natural light while minimizing solar heat gain, thereby enhancing energy efficiency.
With healthcare rapidly advancing, the expansion of the Mayo Clinic campus in Phoenix required a highly coordinated approach to medical facility construction on an active site. Rather than developing on a greenfield, this project had to integrate new structures, towers, treatment areas, surgical suites, and utility cores into a functioning hospital environment without disrupting ongoing clinical operations. One of the first construction challenges was establishing a secure and phased logistics plan. Construction zones were partitioned from patient access routes using temporary fencing, directional signage, and sound attenuating barriers. Materials and equipment deliveries were tightly scheduled during off-peak hours, and tower crane operations were restricted to specific times to avoid interference with medical helicopter flight paths. Early enabling work involved the relocation of existing utilities, including domestic water lines, oxygen and medical gas conduits, and high-voltage electrical feeders, all of which had to be rerouted through temporary above-ground bypasses to maintain uninterrupted service. Structural systems for the hospital towers used a cast-in-place concrete frame with post-tension slabs, enabling open interior spans suited to evolving clinical layouts. The concrete mix was carefully designed for rapid strength gain to maintain construction pace, with high early strength additives and thermal control measures to avoid cracking. Columns were formed with reusable modular formwork, while floor plates were poured in large sequences using pump trucks and placing booms. Seismic detailing was embedded into shear walls and core walls, given the region's moderate seismic classification and the facility's essential use designation. Mechanical, electrical, and plumbing systems were among the most intricate components of the expansion. A centralized mechanical plant was expanded with additional chillers, boilers, and air handling units, each set on isolated inertia bases to limit vibration transmission to clinical environments. Mechanical penthouses and interstitial floors allowed for horizontal distribution of large ductwork, steam, condensate return, and reverse osmosis water piping. Extensive MEP coordination was performed through clash detection using 3D BIM modeling, ensuring ceiling plenums remained serviceable while also complying with stringent infection control requirements. Medical gas systems were extended from new bulk storage tanks through stainless steel piping networks with orbital welded joints, each one subject to 100% radiographic inspection. Redundant power was supplied by new diesel generator banks, paralleled with existing infrastructure, and backed by automatic transfer switches and battery UPS systems located in dedicated electrical rooms. Isolation panels, surge protectors, and clean power transformers were also installed for sensitive imaging equipment. Interior construction was sequenced to align with medical equipment installation schedules. Lead-lined walls and shielded ceilings were placed in radiology and surgical rooms, while vibration-isolated slabs and RF shielding were installed in MRI suites. Finishes included seamless epoxy flooring, antimicrobial wall protection, and hospital-grade ceiling systems with integrated lighting and air diffusers. Infection control risk assessments governed every phase, with negative pressure containment zones, HEPA filtration, and daily clean protocols enforced throughout active areas. Exterior elements incorporated high-performance glazing, architectural precast panels, and metal screen walls to conceal rooftop equipment. Site work included new patient drop-offs, staff parking, and ambulance circulation paths, all coordinated with civil stormwater infrastructure and ADA-compliant design. Ultimately, the Mayo Clinic Phoenix expansion merged complex medical infrastructure with construction excellence to produce a world-class facility that continues to evolve in parallel with modern healthcare delivery. In the rapidly evolving world of electric vehicle manufacturing, nothing has jolted the American industrial sector more than China's audacious BYD megafactory rising in Zhengzhou. This massive complex, scheduled for completion in 2026, is not just a car plant. It is an entire city of automation, logistics, robotics, and scale that utterly eclipses anything under development in the United States. Even in Detroit or Fremont, there is no comparable project on the books, let alone in progress. China is building what amounts to a self-contained EV ecosystem, while the US continues to retrofit aging plants and squabble over battery supply chains. The factory footprint itself is staggering, covering several square kilometers of meticulously planned production, testing, and research areas. It is designed not only to produce over 1 million electric vehicles per year, but to do so with a level of vertical integration that American manufacturers have largely abandoned. Everything from raw material intake to battery cell assembly, body stamping, painting, motor construction, and final vehicle assembly is being consolidated into a streamlined flow that minimizes logistics redundancy. Unlike the US model, which often relies on scattered Tier 1 and Tier 2 suppliers across state lines or even continents, BYD is building an end-to-end supply chain within a single fortified industrial perimeter. The United States is watching with a mix of awe and resignation. The speed with which the Zhengzhou megafactory has gone from approval to foundation work and into structural assembly is nearly inconceivable in North America. In the US, a similar facility would be mired in environmental hearings, zoning disputes, utility negotiations, and political grandstanding. BYD, on the other hand, coordinated regional infrastructure upgrades, roads, rail links, and power grid expansions in parallel with factory construction, avoiding the inefficiencies that plague even the most well-funded US auto projects. Inside the complex, the engineering choices lean heavily toward modularity and future-proofing. High-capacity clean rooms for battery production are being installed with robotic atmospheric sealing and nitrogen supply loops, features that US factories still consider cutting edge. The stamping presses, sourced domestically in China, are capable of near-continuous operation with predictive maintenance systems that operate on an industrial Internet of Things backbone. Conveyor lines span hundreds of meters in fully enclosed, climate-controlled tunnels that feed directly into assembly hangars lined with fleets of synchronized robotic arms. And perhaps most astonishing to observers in the West, this isn't even BYD's only mega factory. China is executing multiple projects of this magnitude simultaneously across the country, while the US still struggles to break ground on its few planned gigafactories. The Zhengzhou facility is simply the most visible tip of a much larger, strategically coordinated manufacturing overhaul that positions China not just as a global EV powerhouse, but as the uncontested epicenter of industrial engineering. When the BYD Megafactory in Zhengzhou opens its doors in 2026, it won't just be building cars, it will be manufacturing the future. And it will do so with a speed, precision, and scale that has left American engineers and policymakers stunned. While the US reflects on its fading industrial might, China is redefining what a manufacturing hub can be, executing in years what would take America decades, if it ever happened at all.
The Javits Center expansion project in New York City was a transformative construction endeavor that significantly increased the capacity and functionality of the Jacob K. Javits Convention Center, one of the largest such facilities in the northeastern United States. The expansion added more than 1 million square feet of space, including exhibit halls, meeting rooms, a rooftop pavilion, and a state-of-the-art truck marshaling facility. Executed on a constrained urban site adjacent to the Hudson River and operating rail lines, the project required a combination of advanced structural engineering, phased logistics, and sustainability-driven design. The initial phase of the project focused on extensive site preparation. This involved clearing the western portion of the existing property, relocating underground utilities, and driving piles for the building foundation. The ground conditions included fill material and soft soils, necessitating the use of deep foundation systems. Steel H-piles were driven to refusal into glacial till and bedrock to support the new superstructure. These piles were then capped with reinforced concrete pile caps interconnected by grade beams, forming a stable platform for vertical construction. The expansion superstructure was designed using a steel frame system, chosen for its strength-to-weight ratio and speed of erection. The main exhibition hall required long-span roof trusses capable of supporting overhead rigging loads for events while providing a column-free interior. These trusses were assembled on-site and lifted into place using crawler cranes with high lifting capacity. The structural steel frame included moment-resisting connections to resist lateral loads from wind and seismic forces, supplemented by braced frames where architectural design permitted. The exterior envelope of the building was constructed using a unitized curtain wall system featuring high-performance glass and aluminum framing. The glass panels were fabricated with low emissivity coatings and frit patterns to control solar gain and reduce glare within the exhibition spaces. The building envelope also incorporated insulated metal panels and rain screen cladding, supported by subgirts attached to the structural frame. A continuous air barrier and vapor retarder were integrated behind the facade to ensure thermal performance and prevent moisture intrusion. One of the central features of the expansion was the truck marshaling facility, which included 4 levels of enclosed, climate-controlled space designed to accommodate up to 200 trucks. This facility was constructed using post-tensioned concrete slabs supported by concrete columns and shear walls. The structural system was engineered to carry heavy live loads and included clear spans and high ceilings to facilitate truck maneuvering. A vehicle guidance system was installed to optimize truck flow and minimize idling times. Vertical transportation throughout the expanded center was provided by multiple banks of elevators and escalators. Freight elevators with oversized cabs and high load ratings were installed to move large exhibits and equipment between levels. Passenger elevators and escalators were placed in high-traffic areas to support efficient movement of attendees and staff. All systems were integrated into a building-wide control system for monitoring and maintenance. Mechanical, electrical, and plumbing systems were designed to meet the demands of large-scale events. Air handling units were placed on mechanical floors and connected to a network of ductwork, with variable air volume boxes to provide zoning control. Chilled water and heating hot water were supplied from a central energy plant using high-efficiency chillers, boilers, and heat exchangers. Building automation systems controlled temperature, humidity, and ventilation in real time. Electrical distribution included new switchgear, step-down transformers, and emergency power via diesel generators and uninterruptible power supplies. The expansion also included a rooftop pavilion and terrace which doubled as a green roof and outdoor event space. This area was built using lightweight structural systems to reduce loading on the roof deck and included pavers on pedestal supports, planting beds, and integrated lighting. Stormwater runoff from the roof was captured and stored in underground cisterns for non-potable reuse, such as irrigation and cooling tower makeup water. Photovoltaic panels were installed to contribute renewable energy and offset utility consumption. Interior construction of the exhibition and meeting spaces emphasized durability, flexibility, and acoustic performance. Raised floors were used in selected areas to allow for reconfigurable power and data connections. Operable partitions divided large meeting rooms into smaller breakout spaces, with acoustic insulation to minimize sound transfer. Finishes included terrazzo, carpet tile, and gypsum board with high recycled content, all selected to meet LEED certification criteria. A major component of the construction effort was the integration of the expansion with the existing Javits Center. This required selective demolition of exterior walls and structural elements, followed by tie-ins to existing mechanical and life safety systems. Phased construction ensured that the existing facility remained operational throughout the project. Temporary partitions, rerouted utilities, and interim egress paths were deployed to maintain safety and functionality. Situated in the heart of Southeast Texas's industrial corridor, the Golden Triangle Polymers project represents a major advancement in the Gulf Coast's petrochemical manufacturing capacity. This massive facility is being constructed to produce polyethylene and other polymer products from ethylene feedstock derived from natural gas liquids. The project begins with the development of a multi-acre greenfield site, requiring extensive earthwork, drainage management, and foundation preparation across terrain with high groundwater and soft, compressible soils. Soil stabilization techniques include the use of lime or cement treatment and surcharge fills to achieve acceptable bearing capacities for large process structures. Deep foundation systems are essential to support the heavy loads imposed by vertical vessels, reactor units, and compressor modules. Construction crews install drilled piers and driven piles to depths exceeding 100 feet, with precision tolerances ensured through the use of GPS-guided rig systems and real-time monitoring during installation. Once foundations are completed, concrete pads and structural steel framing are erected to house process units such as cracking furnaces, separation columns, and polymerization reactors. These are built using modularized construction strategies, where large components are fabricated off-site, shipped by barge or heavy-haul truck, and lifted into position by crawler cranes with lifting capacities over 1,000 tons. The core production process centers around the ethane cracking furnaces, which convert ethane into ethylene through high-temperature thermal decomposition. These furnaces are complex assemblies of fireboxes, radiant tubes, and convection sections, all requiring precise refractory lining and thermal insulation. The resulting ethylene gas is rapidly quenched and routed to distillation columns where it is separated from byproducts under carefully controlled pressures and temperatures. Polymerization units downstream transform ethylene into polyethylene pellets through catalyst-induced chain reactions inside high-pressure reactors. These areas are designed with extensive piping, instrumentation, and control systems to maintain strict process parameters. Each reactor line is supported by a network of utility systems, including nitrogen generation, compressed air, cooling water, and steam distribution, all interconnected through color-coded pipe racks spanning hundreds of feet. Electrical power for the facility is delivered via high-voltage substations and switchgear buildings, incorporating redundant feeds and uninterruptible power supplies for critical control and safety systems. Distributed control systems and programmable logic controllers operate from a central control room, managing process sequencing, alarms, and interlocks. Fiber optic networks connect instrumentation throughout the site to provide real-time monitoring and diagnostic capabilities. A significant part of the construction effort is dedicated to environmental compliance and emissions control. Flare systems, vapor recovery units, and wastewater treatment plants are installed to capture and process effluents, ensuring the plant meets federal and state environmental standards. Additionally, fire protection systems, including foam suppression, hydrants, and emergency deluge zones, are integrated throughout the site to mitigate risks associated with flammable materials. Upon completion, commissioning and startup procedures involve comprehensive testing of mechanical systems, loop checks of instrumentation, safety interlock validation, and initial product runs under controlled conditions. The Golden Triangle Polymers project, once operational, will stand as a cornerstone in the region's industrial landscape, combining large-scale chemical engineering with advanced construction practices and operational precision. From the foundation to the rooftop, every phase of the 1000 Museum's construction demanded attention to detail, precision, and innovative engineering. It stands not just as an architectural landmark, but as a testament to what is achievable when complex geometry, structural necessity, and construction craft are woven together into a seamless vertical composition. Few transportation projects in recent American history, construction of entirely new track alignments through dense urban areas, sensitive wetlands, and heavily trafficked transportation zones. From the earliest design phase, engineers had to account for a range of technical challenges, from grade separation and drainage to noise mitigation and high-speed signaling integration. In contrast, the northern portion from West Palm Beach to Orlando International Airport involved new greenfield construction through undeveloped terrain. Crews cleared and grubbed hundreds of acres, rerouted surface water channels, and installed wildlife crossings in environmentally sensitive areas. Earthwork was extensive. Embankments and cut sections were designed to minimize gradients and allow for smooth acceleration and braking curves. The right-of-way was protected by a combination of fencing, access controls, and overpasses to eliminate at-grade crossings, critical for both safety and operational efficiency. Bridges and viaducts represented key components of the alignment, especially at major road crossings and river spans. Precast concrete girder bridges were deployed using accelerated bridge construction techniques. Piers were founded on deep-drilled shafts, many of which had to be constructed under challenging conditions involving soft soils and high groundwater levels. Certain elevated sections used segmental box girders cast in place and post-tensioned, allowing for long spans and reduced support footprint. These elevated guideways also helped mitigate environmental impact in flood-prone areas and reduce the need for extensive land acquisition. One of the most technically intensive elements was the implementation of a positive train control system across the corridor. This safety-critical layer included continuous GPS-based tracking, wireless communication between locomotives and control centers, and real-time enforcement of speed limits and signal compliance. Installation of the PTC system required the placement of signal houses, transponders, and fiber optic cable across the entire alignment, with redundant power sources and cybersecurity protections. The stations themselves, including the flagship terminals in Miami and Orlando, were designed as integrated multimodal hubs. Structural systems utilized long-span steel framing, while architectural cladding included aluminum composite panels, unitized glass curtain walls, and impact-resistant fenestration. Each station featured elevated platforms to streamline boarding, high-capacity vertical circulation elements, and advanced passenger information systems. Subgrade mechanical spaces housed electrical switchgear, HVAC chillers, filters, and water reuse systems, all connected to centralized building management controls. Rolling stock was procured with an emphasis on energy efficiency, aerodynamic performance, and crash energy management. The train sets featured articulated cars with distributed traction motors, regenerative braking systems, and pressure-sealed cabins. Maintenance facilities along the corridor were equipped with drop pits, wheel lathes, and overhead cranes to support long-term fleet servicing. Throughout construction, scheduling and logistics were as crucial as engineering. Major portions of the corridor were built in active freight environments, requiring overnight possessions and strict coordination with existing operators. In urban areas, construction teams employed traffic diversion plans, temporary decking systems, and vibration monitoring to mitigate disruption to surrounding infrastructure. Environmental compliance was maintained through erosion control plans, wildlife monitoring programs, and wetland mitigation strategies. Ultimately, the completion of the Brightline Miami-Orlando high-speed rail line stands as a testament to integrated transportation engineering, blending high-performance rail systems with modern construction methodologies. The project not only introduces a new mode of inner-city travel, but also sets a precedent for how private investment and infrastructure innovation can reshape mobility across regional scales.
Launching the Scottsdale Optima McDowell Mountain Village meant executing a large-scale, multi-building residential and mixed-use development in a sensitive desert environment, where sustainability, structural innovation, and logistical precision had to align from day one. Unlike conventional suburban construction, this project followed an integrated design-build model that required close coordination between architectural vision and structural implementation, from schematic design through vertical completion. Construction began with extensive site grading across the large footprint, but it also incorporated bioswale integration and retention basins to manage stormwater naturally. Earthwork included over-excavation beneath all building pads, followed by moisture conditioning and recompaction to meet strict geotechnical tolerances. Trenching for deep utilities came next, with parallel routing for chilled water, domestic water, fire protection, sewer, storm, and dry utilities such as power and communications. These were run in pre-planned corridors to serve each building efficiently without unnecessary excavation duplication. Optima's construction model leverages cast-in-place concrete systems extensively, and this village was no exception. Each residential tower utilized a podium-plus configuration, with subterranean parking garages acting as structural base levels. These below-grade levels were waterproofed with bentonite sheets and fluid-applied membranes before forming walls with high-density plywood systems. Vertical columns and shear walls extended through the podium to support the elevated post-tensioned slabs above. These slabs were poured in sequence using high-strength concrete, tensioned after curing to reduce cracking and allow thinner slab profiles, thereby reducing structural dead load and permitting taller floor-to-ceiling heights. Vertical cores for stairs, elevators, and utilities were slip-formed to accelerate progress, allowing parallel trades to begin rough-ins shortly after slab placement. Once the podium was completed, tower levels were constructed floor by floor in a tightly managed schedule. Mechanical, electrical, and plumbing trades were embedded early in the structure, using sleeve boxes, conduit blockouts, and prefabricated pipe racks lifted into place by tower crane. All ductwork was modeled using clash detection software, and fire-rated assemblies were coordinated with penetrations for seamless inspection approvals. Perhaps most distinctive was the incorporation of extensive rooftop gardens and planted balconies, all of which required complex structural planning to support soil loads, waterproofing protection, and integrated irrigation systems. A layered green roof assembly included root barriers, drainage mats, lightweight planting media, and capillary irrigation tubing tied to centralized water treatment systems that filtered grey water for non-potable reuse. Glazing systems were high-performance, thermally broken aluminum frames with low emissivity glass, designed to optimize daylighting while minimizing solar gain. Operable windows were integrated throughout, paired with sunshades, trellises, and balconies that added passive cooling elements. Exterior finishes blended textured concrete, steel mesh panels, and composite cladding materials, applied using suspended swing stages and mast climbers. Interior units followed a luxury specification with radiant floor heating systems embedded in gypcrete topping slabs, integrated lighting control systems, and floor-to-ceiling window walls. Amenities such as fitness centers, lap pools, spa zones, co-working lounges, and automated parking systems were incorporated directly into the podium and terrace levels, requiring close coordination between structural, architectural, and specialty contractors. All buildings were tied together with a shared energy and connectivity spine, linking data, security, fire alarm, and mechanical system controls through a centralized plant and digital management hub. The result was a self-contained, high-density residential complex that not only met structural and livability goals, but elevated the standard for sustainable urbanism in the Scottsdale region. Even in a country saturated with super tall structures, Golden Finance 117 in Tianjin stands apart, not just for its sheer height, but for the boldness of its design and the unapologetic ambition behind it. When completed in 2026, this towering vertical prism will soar over 590 meters into the sky, instantly ranking among the tallest buildings on Earth. For observers in the United States, the project is a striking reminder of just how far China has surged ahead in skyscraper engineering, while America clings to an aging skyline that hasn't fundamentally evolved since the 20th century. Unlike most Western skyscrapers, which are confined by historical districts, union constraints, or antiquated fire codes, Golden Finance 117 represents a new era of structural experimentation and engineering agility. The tapering diamond-shaped profile, for example, is not just a visual statement, it is a carefully calculated aerodynamic solution to reduce wind shear and vortex shedding, both of which pose critical challenges at this height. American cities, meanwhile, are still refining glass cladding systems and worrying about pigeons nesting in HVAC grills. The contrast is impossible to ignore. Structurally, the tower's reinforced concrete core is surrounded by a dense exoskeleton of diagonal steel braces and mega columns, forming a hybrid system that maximizes lateral stiffness and load distribution while preserving open floor plates for high-end commercial tenants. In seismic zones like Tianjin, this kind of approach is non-negotiable. But what's remarkable is the degree of vertical integration in the construction supply chain. Chinese crews fabricated much of the steel locally, shipped it in custom configurations to reduce on-site welding, and used GPS-guided cranes to slot sections together like a vertical jigsaw puzzle. Compare that to the US, where even mid-rise buildings are delayed due to international steel shortages or port delays. Elevator systems inside Golden Finance 117 will redefine vertical mobility. Double-deck high-speed elevators are engineered to travel at speeds exceeding 10 meters per second and utilize regenerative braking systems that feed power back into the grid. Another feature rarely seen in American buildings, where even modest modernization of elevator banks can take years to approve and fund. Integrated smart building controls will manage climate, lighting, security, and occupancy levels with millisecond responsiveness, creating an environment that is as efficient as it is opulent. While the US focuses on LEED certifications and carbon offset promises, China is simply embedding sustainability into the DNA of its structures. Golden Finance 117 will feature greywater recycling systems, insulated facade assemblies, and AI-managed HVAC zoning, all executed not as future upgrades, but as baseline specifications. It's a level of foresight and technical implementation that American developers can only dream about, hamstrung by fragmented contractors, risk-averse financiers, and rigid municipal building codes. By the time Golden Finance 117 opens its doors in 2026, it will stand not just as a monument of Chinese engineering, but as a literal skyline verdict on the state of American decline in the megastructure realm. While the US continues to rezone parking lots and debate high-rise shadows, China is rewriting the vertical blueprint, building higher, faster, smarter, and most of all, without hesitation.
The Hudson Tunnel Project, part of the broader Gateway program, represents one of the most critical infrastructure efforts in the northeastern United States, designed to create a new two-track rail tunnel beneath the Hudson River connecting New Jersey to Manhattan. This massive undertaking involves constructing an entirely new tunnel system, rehabilitating the existing North River tunnels, and upgrading related infrastructure to enhance capacity, reliability, and resiliency for Amtrak and New Jersey transit operations. Given the complexity of tunneling beneath a river in a densely urbanized corridor, the project requires advanced geotechnical planning, innovative construction methodologies, and rigorous logistical coordination. The construction of the new Hudson Tunnel begins with the establishment of tunnel portals on both the New Jersey and Manhattan sides. On the west side, in North Bergen, site preparation includes clearing a large staging area, relocating utilities, and driving deep foundations for the tunnel entrance structure. This involves the use of soldier piles and lagging systems to create excavation support for the open-cut sections of the tunnel approach. The excavation is conducted in phases, with groundwater control measures such as weld points and deep wells installed to stabilize the soil and lower the water table. On the Manhattan side, the tunnel emerges beneath Hudson Yards, requiring intricate coordination with existing foundations, utilities, and operational rail infrastructure. Access shafts and launch boxes are constructed using slurry wall and secant pile techniques to create watertight enclosures. These structures serve as both tunnel access points and critical infrastructure for ventilation and emergency egress. Dewatering systems and continuous monitoring are essential throughout the excavation process to prevent settlement or structural damage to nearby buildings. The main tunnel drive is carried out using pressurized face tunnel boring machines, or TBMs, specially designed to operate in mixed face conditions comprising soft soils, silts, and bedrock. Each TBM is equipped with a rotating cutter head, shield, and trailing support systems that handle spoil removal, segment installation, and auxiliary systems. The TBMs are launched from the New Jersey side, advancing eastward beneath the Palisades, the Hudson River, and into Manhattan. As the machines progress, they install precast concrete segments to form the tunnel lining. Each ring comprises several curved segments with waterproof gaskets bolted and grouted in place to create a continuous sealed tunnel shell. Spoil material generated by the TBMs is transported via conveyor belts or muck trains to the portal areas for removal and disposal. The tunnel boring process is carefully monitored using automated systems that track TBM position, face pressure, cutter wear, and ground movement. Data is relayed to control rooms where engineers can adjust parameters in real time to optimize performance and mitigate risks. Once the twin bores are completed, a range of secondary construction activities takes place inside the tunnels. This includes the installation of track bed systems, drainage lines, utility conduits, and concrete walkways. A concrete invert is poured to create a flat surface for ballastless track systems, typically slab track, which ensures high-speed stability and reduced maintenance. Third rail or overhead catenary supports are anchored to the tunnel lining, depending on the electrification method used. Signal cable trays, fiber optic communication lines, and fire detection systems are integrated along the tunnel interior. Mechanical and electrical systems include powerful ventilation fans housed in dedicated shafts, designed to maintain air quality during regular operations and to evacuate smoke in the event of fire. Emergency lighting, evacuation signage, and public address systems are installed throughout the tunnels, with cross passages between bores spaced at regular intervals to facilitate emergency egress and firefighting access. At each tunnel portal, substations and switchgear are constructed to supply power to trains and tunnel systems. These facilities include redundant transformers, switchboards, and backup power sources such as diesel generators and uninterruptible power supplies. The entire tunnel is connected to a centralized control system that monitors train movement, environmental conditions, and system performance in real time. Simultaneously with the construction of the new tunnel, the project involves the future rehabilitation of the existing North River tunnels, which suffered saltwater damage during Hurricane Sandy and continued to degrade. Once the new tunnel is operational, rail traffic will be rerouted through the new bores, allowing the old tunnels to be taken offline sequentially for full restoration. This process includes the removal of deteriorated track systems, replacement of corroded bench walls, structural repairs to the concrete liner, installation of modern waterproofing membranes, and upgrades to all mechanical and electrical systems. The Hudson Tunnel project also incorporates track realignments and yard reconfigurations on both sides of the river. In New Jersey, additional work includes the construction of approach structures and flyovers to integrate the new tunnel into existing Amtrak and NJ transit lines. In Manhattan, the connection involves carefully threading the new tracks into Penn Station's complex and congested rail throat. This necessitates new signal interlockings, turnout installations, and extensive coordination with other rail improvement projects in the area. Environmental mitigation measures are implemented throughout construction to protect water quality, air quality, and adjacent ecosystems. These include sediment control barriers, air filtration for construction sites, and noise suppression systems. Special consideration is given to minimizing disruption to local communities and existing transportation networks. At the heart of downtown Austin, the Texas Capitol Complex Phase 2 represents a continuation of a multi-year development plan to expand and modernize state government infrastructure while respecting historical context. Construction activities begin with meticulous site logistics planning to accommodate the urban setting, including traffic control, pedestrian rerouting, and staging areas for heavy equipment within a dense government district. Selective demolition of outdated facilities and parking structures clears the way for excavation, utility relocation, and deep foundation work. Excavation reaches depths sufficient for multi-level underground parking and utility corridors. During this phase, crews deploy soil shoring systems using soldier piles and lagging or secant wall methods to ensure trench stability and protect adjacent buildings from settlement or vibration. Dewatering systems with sump pumps and well points are installed to maintain dry conditions during substructure construction. Concurrently, new utility infrastructure, chilled water lines, electric duct banks, and storm drainage systems are embedded in concrete-encased trenches. Structural concrete operations dominate the next phase, with mat foundations poured in multiple continuous placements to support new office towers. Tower cranes are erected early to facilitate vertical construction, hoisting rebar bundles, formwork panels, and precast components. Floor slabs are formed using a combination of post-tensioned and reinforced concrete techniques to optimize span lengths and reduce floor thickness. Core walls housing elevators, stairwells, and mechanical shafts are formed with slip-form systems to accelerate vertical progress while maintaining structural alignment. Above grade, architectural precast concrete panels are installed as part of the building envelope. These panels incorporate design motifs inspired by the adjacent Capitol and blend with the surrounding architectural aesthetic. Window systems include energy-efficient glazing and aluminum framing with integrated sunshades. Mechanical, electrical, and plumbing systems are integrated into each floor through overhead coordination with BIM modeling to avoid clashes and maximize efficiency in confined ceiling spaces. A key element of the project is the expansion of the Texas Capitol Mall, which introduces pedestrian green space atop underground parking decks. This requires careful waterproofing, drainage layering, and placement of structural soil to support landscaping elements. Trees, lighting, benches, and pathways are installed using detailed site plans to ensure ADA compliance and long-term durability. Interior finishes follow close behind structural completion, including raised flooring for cabling flexibility, modular wall systems, acoustic ceiling panels, and high-efficiency HVAC controls. Security systems, IT infrastructure, and life safety features are tested during commissioning. When completed, Phase 2 adds critical state office space, enhances connectivity through walkable corridors, and reinforces the ceremonial axis of the capital with modern construction methods and sustainable design. Amid Florida's subtropical flatlands, the construction of Babcock Ranch Solar Town set out to prove that sustainable urban planning and utility-scale renewable energy could coexist in a master-planned community from the ground up. The project began with a rigorous environmental assessment of over 17,000 acres, ensuring that the development footprint would minimize disruption to existing wetlands and wildlife corridors. Extensive hydrological modeling was undertaken to manage the region's natural water flow patterns, with key areas set aside as conservation zones and integrated into the town's stormwater infrastructure. Once the primary civil grading was complete, roadways, utilities, and fiber optic communication lines were laid in tandem using a trench and backfill system coordinated through GPS-enabled machine guidance. Electrical distribution, unlike in most traditional developments, was built with solar generation as the core, not the supplement. Massive photovoltaic fields were constructed just outside the residential core, spanning hundreds of acres. The solar array used fixed tilt panels mounted on driven steel piles, with underground cabling channeling direct current electricity to inverters and step-up transformers before feeding into the regional grid. Residential construction throughout Babcock Ranch adhered to rigorous energy efficiency and wind resilience standards. Homes were built with insulated concrete form walls, impact-rated glazing, radiant barrier roof sheathing, and deep roof overhangs to mitigate solar gain. Roofing materials were chosen for their reflectivity and durability, including metal and tile products designed to exceed hurricane uplift requirements. Mechanical systems included high-SEER HVAC units, advanced dehumidification control, and smart thermostats integrated into home automation networks. What differentiated the town further was the full integration of microgrid technology. Battery storage facilities, housed in climate-controlled steel enclosures, provided grid balancing and backup capabilities. These systems ensured continuous power delivery even during grid disturbances and could island the town if necessary during extreme weather events. Switchgear, transformers, and substations were elevated on reinforced concrete pads with flood-proof enclosures and remote diagnostic sensors to prevent failure during high water levels. Public buildings and amenities, including schools, commercial centers, and community centers, were constructed using a design-build delivery method to ensure consistency in green building standards and rapid delivery. All structures were wired for net metering, demand response control, and energy use feedback systems. Building envelopes featured continuous insulation, reflective membranes, and operable windows for cross-ventilation, where applicable passive cooling elements such as overhangs, louvers, and vegetative shading were incorporated into the architecture. Pedestrian infrastructure was planned ahead of vehicular design, with wide pathways, permeable paver systems, bioswales, and shade structures forming the connective tissue of the community. Stormwater is handled via a series of vegetated retention basins and interconnected canal systems, which serve dual purposes of flood mitigation and habitat support. Water and wastewater treatment systems were decentralized and included reclaim systems for irrigation, with smart meters installed throughout to promote conservation.
Not every freeway expansion challenges engineers with such extreme topographic variation as the Interstate 17 Black Canyon Freeway widening. This project, traversing from North Phoenix up through mountainous terrain toward Flagstaff, required overcoming both urban congestion constraints and rural geological complexities. It was not a uniform widening effort. Rather, it entailed a hybrid approach of adding general-purpose lanes, climbing lanes for freight vehicles, and in some segments, reversible flex lanes designed to accommodate peak traffic flow. Construction sequencing began with extensive earthwork, particularly through the northern sections where cuts into basaltic rock were necessary. Controlled blasting operations were scheduled in tightly regulated windows to reduce traffic disruption and environmental impact. Each blast zone underwent pre- and post-blast surveys to ensure rock stability and confirm that the blast radius remained within safety thresholds. Debris was excavated using high-reach excavators and loaded into articulated dump trucks for repurposing as fill in adjacent embankment zones. These embankments were constructed in compacted lifts, each tested for moisture content and density to meet strict compaction standards necessary for load-bearing capacity. In the more urbanized southern corridor, work was performed in narrow medians and shoulders. Traffic staging required temporary barrier placement, restripping, and real-time signal adjustments to maintain throughput while isolating work zones. Construction of new lanes meant full-depth pavement installation, beginning with subgrade preparation, placement of aggregate-based course, and then successive lifts of asphaltic concrete. The mix design was tailored for durability in high-temperature conditions, incorporating polymer-modified binders and performance-graded asphalt to resist rutting and thermal cracking. Bridges posed a significant element of the widening effort. Many existing structures over washes and arterial roads were widened symmetrically using cast-in-place concrete decks over precast, pre-stressed concrete girders. Abutments and piers were reinforced with drilled shaft foundations, extending deep into competent bedrock to mitigate differential settlement. Expansion joints, bearing pads, and shear keys were detailed to accommodate seismic and thermal movements while maintaining deck continuity. Stormwater management infrastructure was upgraded in tandem, involving the installation of reinforced concrete box culverts and oversized pipes beneath the widened footprint. In some areas, detention basins were excavated with engineered outlet structures to manage discharge rates and protect downstream properties from flooding. Erosion control measures, including soil binders, riprap armoring, and hydro seeding, were deployed along slopes and drainage channels as permanent stabilization. Intelligent transportation systems were embedded throughout the corridor. This included dynamic message signs, closed-circuit TV cameras, radar-based traffic sensors, and fiber optic communication backbones. These systems were linked to the Regional Traffic Operations Center, enabling real-time monitoring and adaptive traffic management, particularly useful for managing incidents and peak period congestion. Guardrail systems, median barriers, and high-visibility signage were installed during the final phase. Road striping used thermoplastic materials with reflective beads for enhanced night visibility. Before opening, each section underwent load testing, profile evaluation, and friction testing to ensure geometric and safety compliance. It's not every day that an entire city rises from scratch, built not around sprawl and car dependency, but around integrated infrastructure, ecological balance, and digital governance from the ground up. Yet that's exactly what is happening in Hebei province with the creation of the Xiong'an New Area, a project so ambitious in scope and speed that it has stunned urban planners and civil engineers in the United States. Slated for full-phase completion by the early 2030s, with major infrastructural milestones arriving before 2030, Xiong'an isn't just a city, it's a systems-level reimagining of urbanism on a scale the US hasn't attempted since the founding of Washington, D.C., and even that pales in comparison. The planning phase alone set off alarm bells in American think tanks. China is building a technologically integrated city across hundreds of square kilometers of former farmland and wetlands, designed to absorb administrative functions from Beijing, support over 2 million residents, and operate entirely on smart infrastructure platforms from day one. The US, by contrast, can barely streamline broadband access in its own capital, let alone build a futuristic urban environment with climate-adaptive architecture, autonomous public transport networks, and digitized municipal services hardwired into its very foundations. What makes Xiong'an particularly shocking to US observers is how China is using the full weight of national coordination to push the project forward. Every utility trench, bridge, subway tunnel, and energy grid segment is part of a central master plan managed by vertically integrated design and construction units. In America, such coordination between federal, state, and local agencies remains elusive, and city-scale projects often die under the weight of conflicting jurisdictions. In China, earthworks, underground infrastructure, smart grid deployment, and data center integration all unfold simultaneously under one mandate. Construction in Xiong'an follows a bottom-up sequencing model rarely executed at this scale. The entire underground city, a two-level subterranean corridor system housing freight traffic, utilities, and service access, was prioritized before any superstructure went up. This allowed surface-level urban life to be planned around green corridors, pedestrian movement, and above-ground public transit, rather than being retrofitted awkwardly after the fact, as is typical in the US. American cities still wrestle with rerouting sewer lines built a century ago. In Xiong'an, fiber optics, stormwater management, and autonomous delivery routes are embedded before the first office tower breaks ground. Perhaps most humiliating to American infrastructure observers is the speed. What takes US cities a decade just to zone and review, Xiong'an has already begun implementing. Schools, hospitals, data hubs, and transportation hubs are operational or near completion before many Americans even learned the city existed. By the time Xiong'an reaches its operational zenith in the next several years, it will not only house over 1 million people, it will do so with climate-neutral energy systems, urban cooling zones, AI-regulated traffic patterns, and full-spectrum digital administration. This is not a utopia drawn on paper. It is a massive engineering reality unfolding with methodical precision, and it serves as a direct challenge to the United States, where aging infrastructure and decentralized governance make such projects nearly unthinkable. While America reflects on what it used to build, China is constructing the future, and cities like Xiong'an prove that they're doing it at a scale and sophistication the US has yet to match.
The construction of One Manhattan Square, a luxury residential skyscraper located on the Lower East Side of Manhattan, required a carefully orchestrated approach to high-rise construction on a waterfront site with challenging geotechnical conditions and limited staging space. Rising over 800 feet in height, the tower features a slender profile and houses hundreds of residential units above a multi-level podium. The project involved extensive subsurface work, a reinforced concrete structural system, curtain wall facade installation, and the integration of extensive mechanical, electrical, and plumbing systems, all within the constraints of a dense urban environment. The first phase of construction focused on site excavation and foundation work. Given the site's proximity to the East River, groundwater management and soil stabilization were critical. Deep excavation was necessary to reach suitable load-bearing strata and accommodate below-grade parking and service levels. A perimeter slurry wall system was constructed to support the excavation and act as a long-term waterproofing barrier. This involved trenching around the site's perimeter, supporting the trench walls with bentonite slurry, and placing reinforcement cages followed by trammy concrete pours to form continuous wall panels. Within the slurry wall enclosure, mass excavation was conducted down to the foundation level. Dewatering systems using well points and sump pumps controlled groundwater intrusion, and real-time monitoring ensured excavation stability. The building's foundation consisted of a thick, reinforced concrete mat slab, designed to distribute vertical loads across the footprint while resisting hydrostatic uplift pressure. The mat was poured in large segments using high-strength concrete with admixtures to enhance durability and control curing. Vertical construction proceeded with the erection of a cast-in-place reinforced concrete superstructure. The building's structural system was composed of a central concrete core housing elevators, stairs, and mechanical risers, surrounded by perimeter columns and shear walls. The core was constructed using a jump form system, allowing continuous vertical progress while floor slabs were cast around it using flying formwork and table forms. Each floor cycle averaged several days with rebar post-tensioning cables and mechanical sleeve penetrations installed prior to concrete placement. High-strength concrete mixes were used to achieve the design compressive strength required for slender tower stability. Lateral loads from wind and seismic activity were resisted primarily by the stiffness of the core and the interaction of shear walls distributed along the tower's footprint. To reduce construction time, Climbing formwork systems and tower cranes were deployed to support material delivery and personnel movement as the building rose. The tower's facade system featured a unitized curtain wall assembly composed of aluminum frames and insulated glass panels with low emissivity coatings. Each panel was fabricated off-site, pre-glazed, and tested for air and water infiltration before delivery to the site. Curtain wall installation occurred concurrently with structural work, with panels hoisted into position and anchored to embedded inserts at slab edges. The panels also included spandrel sections to conceal floor slabs and mechanical systems, providing a continuous visual envelope. Mechanical, electrical, and plumbing systems were routed vertically through dedicated shafts within the core and extended horizontally across each floor plate. The building's HVAC system relied on fan coil units and centralized chillers located in mechanical floors, supported by rooftop equipment and condenser water loops. Fresh air intake and exhaust systems were integrated into the facade using hidden louvers and custom architectural details. Plumbing systems were zoned by floor and included pressure-boosting pumps and backflow prevention devices to maintain consistent service across all levels. Electrical systems included dual utility feeds, on-site transformers, and emergency backup generators. Sub-metering was implemented to track usage by individual residential units, and distribution panels were installed in closets on each floor. Fire protection systems consisted of wet pipe sprinkler systems, standpipes, and fire alarm wiring, all coordinated using building information modeling to avoid conflicts with structure and finish systems. Interior fit-out began once the building envelope was enclosed and permanent power was established. Each residential unit featured gypsum board partitions, sound-rated floor assemblies, and high-end finishes including wood flooring, custom cabinetry, and stone countertops. Kitchens and bathrooms were prefabricated as modular assemblies where possible to accelerate installation and improve quality control. Energy-efficient appliances, LED lighting, and smart home technology were integrated into the units. Amenity spaces were constructed within the building's podium and included fitness areas, lounges, spa facilities, and entertainment rooms. These spaces required specialized mechanical zoning and sound isolation to provide acoustic comfort and performance. Finishes in these areas included acoustic ceilings, soft flooring, and decorative lighting systems. An exterior landscape terrace was built over the podium roof slab, incorporating lightweight fill, waterproofing membranes, and stormwater management features such as planters and drainage mats. Vertical transportation systems included high-speed elevators equipped with destination dispatch technology to reduce wait times and improve traffic flow. Elevator shafts were constructed using slip-form techniques within the core, and guide rails, cabs, and control systems were installed once the structure topped out. Life safety systems were interconnected through a central command center, with emergency lighting, public address systems, and integrated surveillance and access control equipment. Throughout construction, logistics were tightly controlled due to the site's urban setting. Deliveries were scheduled in narrow windows, materials were staged just in time, and vertical hoists and cranes were used to reduce on-site clutter. Coordination with city agencies ensured that street closures, utility connections, and construction access points were managed without disrupting surrounding traffic and pedestrian activity. The Bronx Point development is a transformative mixed-use project situated along the Harlem River waterfront in the South Bronx. Designed to anchor the revitalization of the Lower Concourse neighborhood, this project blends residential housing, public open space, cultural institutions, and retail infrastructure into a cohesive, community-oriented development. The Southeast Connector project in the Dallas-Fort Worth region is a significant transportation infrastructure initiative designed to expand and modernize a key highway corridor to accommodate increasing traffic volumes and improve regional mobility. The construction process begins with detailed geotechnical investigations to assess subsurface conditions across the route. Boreholes and soil sampling guide the design of pavement structures and inform decisions about embankment stabilization, especially in areas with expansive clay or soft subgrades. Initial site work involves extensive utility coordination and relocation, given the presence of underground power lines, fiber optics, gas mains, and municipal water systems. Specialized crews use hydro-excavation and trenchless boring methods to install new utility runs without disrupting surface operations. Simultaneously, the construction zone is cleared of vegetation, existing pavement is milled or demolished, and temporary drainage measures are installed to manage stormwater during earthworks. Mass grading operations utilize GPS-guided bulldozers and scrapers to sculpt new roadway alignments, build embankments, and excavate cut sections through rolling terrain. In low-lying areas, wick drains and surcharge fills are employed to accelerate settlement and enhance long-term subgrade stability. Reinforced concrete box culverts and precast arch structures are installed to span creeks and drainage channels, with erosion control mats and riprap protection placed at inlets and outlets. The highway widening includes adding general-purpose lanes and managed lanes, which requires staged construction to maintain traffic flow. Temporary detours and traffic control devices are deployed in phases, with barrier systems, message boards, and flagging operations ensuring worker safety. Sub-base materials such as lime-treated soil or cement-stabilized base are placed and compacted before successive layers of hot-mix asphalt or continuously reinforced concrete pavement are applied. Bridges along the corridor are demolished and reconstructed with wider spans and higher clearances to meet modern standards. Foundation construction includes driven steel H-piles or drilled shafts depending on soil conditions, followed by the erection of cast-in-place or precast concrete bridge components such as abutments, piers, and girders. Superstructure placement is often conducted during overnight closures to limit traffic disruptions. Sound walls, intelligent transportation systems, lighting, and signage are installed in parallel with the mainline construction. Dynamic message signs, vehicle detection loops, and closed-circuit cameras are connected through fiber optic networks to regional traffic management centers. Upon completion of paving and striping, punch list activities address final grading, landscaping, and system testing before the project is opened fully to public use, significantly enhancing connectivity between southeastern Dallas and central Fort Worth. In the heart of downtown Miami, where the skyline rises in a collage of glass towers, 1000 Museum distinguishes itself not just by height, but by the extraordinary engineering involved in bringing its organic exoskeleton form to life. Long before any concrete was poured, the project demanded a fundamental rethinking of conventional tower design due to the decision to incorporate a curvilinear external structural system. The concept required that the building's primary structural support come from its exterior, a dramatic departure from the more common internal core and column system used in most residential high-rises. The foundation phase began with the installation of deep drilled shafts extending over 100 feet into Miami's sedimentary bedrock. These shafts were reinforced with heavy steel cages and trimly poured concrete to form a stable load path beneath the structure's core and its unique perimeter support zones. Above ground, the ground-level mat foundation included thousands of cubic yards of high-strength concrete, placed in continuous pours to avoid cold joints and ensure structural uniformity. The mat, several feet thick, had to be completed in multiple stages, each meticulously scheduled to coordinate pump trucks, concrete deliveries, and rebar placement. And became the central construction challenge. Rather than simple vertical columns, the perimeter frame was made up of sweeping biomorphic curves that branched and intertwined as they moved up the tower. This required a custom formwork system, fabricated off-site and assembled on-site in pieces, with tolerances often within a fraction of an inch. The forms had to be modified on a floor-by-floor basis due to the shifting geometries, and concrete placement was done in segments with continuous quality monitoring to prevent honeycombing or segregation within the curved shapes. Internal columns. Because the exoskeleton was exposed to the elements, its surface quality had to meet both structural and architectural criteria, requiring special attention during finishing, routing HVAC, plumbing, and electrical lines through a tower with no conventional floor plate repetition required adaptive engineering and close collaboration among trades. A key component of the tower's innovation was the construction of a rooftop helipad, a rare building loads at the highest elevation, along with wind load modeling to ensure rotor wash would not affect facade elements or roof equipment. Below the helipad, mechanical systems including chilled water plants and emergency generators were installed in hardened enclosures, isolated acoustically and vibrationally to avoid disturbing the building's luxury residential interiors. The glass curtain wall system was also a vital piece of the project. It had to be installed around the branching exoskeleton while maintaining weather tightness and minimizing air infiltration. Each panel was custom-shaped and tested for wind resistance, particularly given the building's exposure to hurricane-force conditions. Installation teams used specialized lifting rigs and sequencing plans to coordinate around the exoskeletal nodes, many of which intersected the glass modules in non-linear ways. Elevator and life safety systems at elevators and pressurized stairwells. The building featured advanced smoke evacuation systems and a full backup power architecture integrated into the overall structural system.
Unlike traditional airport projects built in undeveloped areas, the Mesa Gateway Airport expansion required surgical precision to retrofit and expand critical infrastructure within an operational airfield. The effort spanned terminal growth, airside improvements, and upgrades to utilities, all orchestrated under strict Federal Aviation Administration compliance and continuous coordination with airport operations. Initial groundwork focused on expanding the commercial terminal. This involved selective demolition of existing structures and pavement, followed by deep trenching to relocate utility lines such as jet fuel piping, communications fiber, and storm drains. Excavation was staged to avoid conflicts with active taxiways and required trench shielding, dewatering pumps, and utility phasing plans that prevented disruption to existing airport services. Potholing and ground-penetrating radar scans were performed to identify undocumented legacy utilities from the site's previous military use. Terminal expansion required a structural system that combined steel moment frames with composite decking, supported by drilled piers tied into deep foundation beams. The steel frame was erected using high-reach cranes that were coordinated with the airport's control tower to avoid airspace intrusion, particularly during girder lifts near the active apron. Roof decking was fireproofed with sprayed-applied materials, and roof insulation assemblies were capped with a single-ply membrane roofing system designed to withstand high desert UV exposure and monsoonal winds. Passenger processing areas were built with forward-looking flexibility. Baggage handling systems were laid out beneath the slab-on-grade level, supported by trench drains and conveyor pits formed with cast-in-place concrete. Conveyor belts, diverters, and scanners were pre-assembled off-site and installed as modules to reduce installation time within a compressed schedule. Check-in counters, TSA security lanes, and automated boarding gate systems were backed by robust data infrastructure routed through overhead cable trays, linked to secure IT closets and network hubs located in protected zones behind the scenes. Airside improvements extended to taxiway extensions and apron reconfiguration. Crews used slip-form paving machines to place Portland cement concrete with dowel joints, constructed in multi-lane widths with tight alignment controls. Concrete batch plant operations had to meet FAA quality standards for airfield pavements, including flexural strength and surface smoothness. New lighting systems, edge lights, taxiway center lines, and approach indicators were installed within pavement cans fed by underground duct banks, all tied into the airport's airfield lighting control system. Jet bridges were added and coordinated with apron regrading to match aircraft door sill heights. Reinforced apron paving with fuel hydrant pits, ground power units, and potable water hookups were integrated at each new gate position, enabling faster turnaround times for commercial airliners. Drainage for apron areas was routed to oil-water separators to maintain environmental compliance before entering the municipal storm system. To support future growth, a new central energy plant was constructed, housing chillers, boilers, backup generators, and water softening systems. Mechanical systems were routed through underground utility corridors leading to terminal mechanical rooms equipped with air handlers, VAV boxes, and HEPA filtration. All critical systems were designed with N+1 redundancy to ensure uninterrupted operation. No one in the American transportation sector expected China to push a high-speed rail corridor straight through some of the world's most hostile, geologically volatile terrain. Yet that is exactly what's happening with the Sichuan-Tibet Railway, specifically its most extreme segment between Ya'an and Ningxi. Scheduled for completion later this decade, this railway isn't just a new line. It's a geopolitical and engineering thunderclap that has left US infrastructure planners completely dumbfounded. While the US continues to struggle over basic high-speed rail concepts in California or the Northeast Corridor, China is carving precision tracks through mountains that American engineers wouldn't even consider penetrable. This section of the Sichuan-Tibet Railway traverses the eastern edge of the Qinghai-Tibet Plateau through a landscape racked by seismic activity, landslides, flash floods, and vertical elevation changes that defy conventional construction logic. From an engineering perspective, it is nothing short of madness. And yet, China is doing it. Over 90% of the route involves bridges or tunnels. The mountains are so steep and the river valleys so narrow that entire segments of track float in space, supported by towering piers driven into fractured bedrock, stabilized with custom-formulated grout mixtures and seismic dampers that adjust in real time. Meanwhile, in the United States, environmental assessments for even modest new lines can stretch across 2 decades. Lawsuits, land acquisition disputes, and lack of central authority all conspire to kill projects before they begin. In China, by contrast, the Ya'an-Ningxi section is being built in synchronized stages with satellite-monitored precision. Tunnel boring machines were airlifted into valleys by heavy-lift helicopters. Entire work camps were constructed at altitude with oxygen-enriched living quarters. Surveying drones and AI-assisted topographic models are guiding every borehole and anchor point. The rail line itself will be a marvel of operational engineering. Designed for high-speed service despite the rugged terrain, the railway includes multiple pressure-sealed passenger compartments to prevent altitude sickness, intelligent rail control systems with predictive braking logic, and anti-icing rail heaters embedded along the route, all while navigating zones with temperature swings of over 30 degrees Celsius in a single day. Nothing even remotely like this exists in the United States, where high-speed rail has remained a political fantasy rather than a technological commitment. One of the crown jewels of this section will be a series of deep-bore tunnels that punch through active fault zones at high elevation. These are not ordinary tunnels. They are lined with adaptive reinforcement systems that can flex and redistribute load during seismic events. In the US, existing tunnels on the East Coast still lack basic fire suppression or modern ventilation systems. The technological gap is growing by the year. Once the Ya'an-Ningxi segment of the Sichuan-Tibet Railway is fully operational, it will tie together regions previously considered logistically inaccessible. The United States, with all its legacy in railroad innovation, has nothing in its pipeline even approaching this level of difficulty or ambition. While American trains still crawl along Civil War-era routes, China is building what can only be described as a continental spinal cord. One tunnel, one bridge, one impossible kilometer at a time.
The redevelopment of Penn Station in New York City is a large-scale infrastructure and architectural initiative designed to transform one of the most heavily trafficked and functionally outdated transportation hubs in the United States into a modern, efficient, and passenger-focused facility. This multifaceted project involves the complete overhaul of existing station elements, integration of new transit connections, and the construction of Moynihan Train Hall as an extension of Penn Station's operational footprint. The redevelopment process unfolded across multiple phases, each requiring intense coordination between civil, structural, mechanical, and transportation engineering disciplines, all while maintaining continuous transit service for hundreds of thousands of daily commuters. The first critical step in the redevelopment was the structural conversion of the James A. Farley Post Office building into the new Moynihan Train Hall. This Beaux-Arts structure, located directly west of Penn Station, was originally constructed with massive granite walls and steel floor framing. Adapting this historic facility to serve as a modern rail terminal required surgical demolition of interior structural elements and the reinforcement of floor slabs and columns to accommodate new loading requirements. The most dramatic transformation occurred with the installation of a vaulted steel and glass skylight system over the former mail sorting room, now repurposed as the main concourse. This skylight was supported by new structural steel arches tied into the existing steel framing through moment-resisting connections. The entire installation had to be designed to accommodate differential settlement, thermal expansion, and seismic movement. Beneath the concourse, platforms and tracks serving Amtrak and Long Island Railroad were upgraded to meet modern standards. This involved improving vertical circulation with new escalators and elevators, reinforcing platform edges, upgrading lighting, signage, and wayfinding systems, and integrating accessibility features in compliance with the Americans with Disabilities Act. The mechanical ventilation systems serving the platforms were also expanded, including the installation of new fans, air shafts, and smoke evacuation ducts. The expansion of concourse areas continued under the streets and buildings adjacent to the existing Penn Station, where new subterranean pedestrian corridors were excavated using a combination of cut and cover and hand mining techniques. These corridors were lined with waterproof concrete and outfitted with finishes that matched the aesthetic of the new train hall. Special care was taken during excavation to protect nearby building foundations and subway infrastructure, employing instrumentation to monitor ground movement in real time. Within the original Penn Station footprint, structural retrofits were carried out to open up the low-ceilinged areas that had long hindered passenger flow and visibility. This included the removal of non-structural mezzanines and drop ceilings, the relocation of HVAC ductwork, and the replacement of outdated mechanical systems. Load-bearing columns were clad with fire-rated materials, and floors were refinished with terrazzo and stone tile to improve durability and appearance. Lighting systems were upgraded to high-efficiency LED arrays, integrated with motion sensors and daylight harvesting controls. A new entrance pavilion was constructed on 7th Avenue, creating a prominent street-level presence for the station. The pavilion consisted of a steel-framed structure with a glass facade supported by tensioned cable trusses. This open and transparent design brought natural light into the concourse and served as a visual counterpoint to the previously closed-off street frontage. Beneath the entrance, new circulation stairs, escalators, and elevators were installed to move passengers from street level to concourse and platform levels with minimal congestion. Mechanical, electrical, and plumbing systems throughout the redeveloped station were completely overhauled. Central utility plants were upgraded with high-efficiency chillers, boilers, and air handling units. These systems were connected to a distributed network of variable air volume boxes and demand-controlled ventilation points designed to adapt to occupancy loads in real time. Electrical distribution was modernized with new substations, transformers, and switchgear capable of supporting expanded digital signage, surveillance systems, and tenant loads. All systems were tied into a centralized building management system with touchscreen controls, alarms, and energy monitoring capabilities. The redevelopment also emphasized sustainability, with features such as green roofing, stormwater management systems, and low-impact construction materials. Green roofs were installed atop portions of the Moynihan Train Hall and the new entrance pavilion, supported by reinforced roof slabs and integrated drainage systems. Stormwater runoff was directed to underground detention tanks and treated before being discharged or reused for non-potable applications such as irrigation. During the course of construction, maintaining uninterrupted train service remained a top priority. Work was scheduled in off-peak hours and overnight shifts to limit disruptions. Temporary barriers, rerouted access paths, and detailed construction phasing plans allowed contractors to isolate active work zones from public areas. Safety was ensured through real-time coordination with Amtrak, Long Island Railroad, and New Jersey Transit, with flagging crews and communication protocols in place for track-level activities. Coordination with existing infrastructure was another critical component of the project. Penn Station interfaces with subway lines, PATH trains, and multiple street-level transportation systems. The redevelopment included improvements to subway entrances, ticketing areas, and passageways connecting the transit systems. Structural ties were established between the old and new facilities, with seismic joints and expansion joints incorporated to account for differential movement between the structures. Serving as one of the largest and busiest airports in the world, the Dallas-Fort Worth International Airport represents a vast and intricately planned transportation infrastructure. The original construction of the airport began with the selection and preparation of an expansive site straddling the cities of Dallas and Fort Worth, requiring extensive grading, drainage systems, and soil stabilization over thousands of acres. Earth-moving operations included the redistribution of millions of cubic yards of soil to establish level runways, taxiways, and terminal zones, while ensuring compliance with strict FAA airfield geometry standards. The runways, which are among the longest in the country, were constructed in multiple phases using layered pavement systems. These include a stabilized subgrade, cement-treated base, and several layers of high-performance concrete capable of withstanding repeated heavy aircraft loads. Each runway incorporates lighting systems embedded in the pavement for approach, edge, and touchdown guidance, connected via underground conduits to airfield lighting control stations. Parallel taxiways are designed for optimal aircraft movement efficiency, with concrete paving sections built using slip-form pavers for tight tolerances and surface uniformity. Terminal construction involved erecting multiple large-scale structures with steel-framed superstructures and curtain wall systems composed of aluminum and high-efficiency glazing. Each terminal is equipped with multiple gate positions, connected to jet bridges, and supported by mechanical systems such as baggage handling conveyors, passenger boarding controls, and HVAC systems designed for high occupancy and variable loads. Subsurface utilities and automated train tunnels were constructed simultaneously, using cut-and-cover and bored tunneling methods to ensure interterminal connectivity without interrupting aircraft operations. The airport includes a central utility plant, constructed with chillers, boilers, and thermal energy storage tanks to provide efficient heating and cooling across the entire complex. Electrical substations and emergency backup generators are integrated into the system for uninterrupted power supply to critical operations such as runway lights, security systems, and air traffic control. To support intermodal transport, extensive roadways, bridges, and parking structures were built using pre-stressed concrete beams and deck slabs. Toll plazas and access control points are integrated with ITS systems for real-time monitoring and traffic regulation. Continuous expansion projects include terminal upgrades, runway extensions, and the integration of sustainability features such as solar panels, stormwater retention basins, and energy-efficient lighting. From a construction and engineering standpoint, Dallas-Fort Worth International Airport is a constantly evolving megastructure requiring phased construction strategies, airside-landside coordination, and specialized materials and systems to support safe and efficient global aviation operations. Starting from its immense foundation work, the construction of Panorama Tower in Miami was an engineering endeavor that pushed the limits of vertical urban development in South Florida. The site preparation required the excavation of a deep foundation mat nearly 10 feet thick, which would ultimately support the enormous structural loads of what became the tallest building in the state. The tower's foundation system relied on a network of auger cast piles extending more than 100 feet below grade, drilled through soft coastal sediments into underlying limestone strata. A high-strength concrete pour of over 13,000 cubic yards was executed in a continuous operation lasting more than 24 hours, involving dozens of concrete trucks in a carefully choreographed rotation. Once vertical construction began, the superstructure rose rapidly using a cast-in-place concrete core system. The central shear walls formed the backbone of the tower, housing elevator shafts, stairwells, and mechanical risers. Surrounding this core, post-tensioned concrete slabs and columns were poured in a cycle of roughly one floor every 4 to 5 days. To maintain this pace, formwork systems were mounted on self-climbing hydraulic jacks, and a just-in-time delivery system kept materials flowing without congesting the tight urban staging area. The building's mix of residential, commercial, and hotel uses demanded varied floor layouts and load-bearing considerations. Transfer girders, some spanning over 30 feet, were integrated at podium levels to redistribute structural loads around open lobby and amenity spaces. These massive concrete beams required temporary shoring towers and custom formwork assemblies, built and dismantled as the structure progressed upward. Mechanical systems throughout the tower had to account for vertical reach, energy efficiency, and hurricane resilience. Multiple chiller plants were stacked vertically at mechanical floors to optimize thermal load distribution. Water pressure zones were engineered using variable speed booster pump systems and brake tanks to maintain consistent pressure throughout the more than 80 stories. The electrical system incorporated dual feeds and emergency backup generation housed on elevated floors to avoid flooding risk. Vertical duct shafts were carefully coordinated with structural elements using 3D modeling tools to prevent clashes. The curtain wall system was engineered for high impact resistance and thermal performance. Each panel included laminated glass, extruded aluminum frames with thermal brakes, and anchoring systems rated for over 170 miles per hour wind loads. Installation occurred using mast climbers and swing stages, starting from the mid-tower levels and working both upward and downward. Balconies were constructed with cantilevered concrete slabs and glass railings carefully sloped to direct water runoff away from the facade. Elevator logistics were especially critical in such a tall structure. High-speed gearless traction elevators with destination dispatch were installed to minimize wait times, and reinforced machine rooms were positioned at intervals to house motors and control equipment. Fire protection systems included pressurized stairwells, zoned sprinkler systems, and smoke control fans, all tied into a centralized life safety command center.
Construction of the VI Resort in Glendale unfolded as a complex hospitality and entertainment project requiring meticulous sequencing across multiple concurrent work streams. Rather than a single structure development, this resort was conceived as a multi-building campus featuring a luxury hotel tower, indoor and outdoor concert venues, water attractions, retail and dining spaces, and a central lagoon, each element demanding its own set of structural and systems engineering approaches. The site preparation phase began with mass excavation to create space for underground parking and mechanical service corridors. Soil stabilization involved lime treatment in select areas to improve load-bearing characteristics, followed by the placement of geotextile fabric and compacted fill. The lagoon basin required a deeper excavation profile, finished with a reinforced concrete liner and waterproofing membrane to contain the water feature without seepage. Adjacent utility trenches were routed to accommodate filtration lines, electrical conduits, and pump intakes, all laid in accordance with hydrodynamic modeling for optimal water circulation. The resort's signature hotel tower rose from a spread footing foundation system tied together with continuous grade beams. Above that, the structural system transitioned to a cast-in-place concrete core with post-tensioned concrete slabs, allowing for long-span floor plates and column-free views for premium guest rooms. Creep and shrinkage of the slabs were modeled early to account for deflection and ensure precise placement of embedded sleeves and anchor points for curtain wall systems. The exterior facade used a combination of unitized aluminum glazing systems and rain screen metal panels installed via swing stage access from the tower's perimeter scaffolding. Simultaneously, the concert amphitheater was constructed with a structural steel skeleton, integrating trusses that spanned the entire stage and canopy area. Acoustic isolation pads and vibration damping systems were embedded into the structure to reduce transfer to the surrounding resort zones. Back-of-house areas included electrical rooms with stage lighting control panels, audiovisual distribution rooms, and dock access for touring vehicles. Amphitheater seating was cast in place in a raked configuration with egress paths designed to flow directly into landscaped promenades. Special attention was paid to the lagoon-side entertainment areas, where boardwalks, cabanas, and overwater structures required deep-driven steel piles and precast concrete caps. These were connected by engineered wood decking that resisted UV exposure and thermal expansion. Integrated lighting and sound systems were embedded into the hardscape with low-voltage conduits routed through waterproof junction boxes mounted beneath structural supports. Mechanical and electrical systems across the site were integrated through a central utility core, with chilled water and emergency power distributed through a looped system. Energy efficiency was prioritized with variable speed drives, economizer cycles, and advanced building automation controls. Each building was modeled thermally to optimize glazing ratios, shading structures, and HVAC zoning. Kitchen exhaust systems, grease interceptors, and commercial water heaters were installed in the back-of-house areas for food and beverage operations. From a distance, the Chongqing International Trade and Commerce Center looks like another skyline-defining tower in a city already overflowing with vertical ambition. But what's rising in Chongqing right now is not just a skyscraper. It's a bold architectural and engineering statement that leaves the United States grasping for comparison. Scheduled for completion in 2027, this super tall project isn't just tall, it's intensely complex, highly integrated, and deeply symbolic of China's new era of urban dominance. For US observers, it's another stark reminder of the growing gulf in technical capacity and megaproject delivery. The tower is designed to push well past 500 meters in height, making it one of the tallest structures in Western China. Yet it's the location and engineering conditions that make this project truly extraordinary. Built in one of the most topographically challenging urban environments on Earth, the structure must anchor itself into hilly terrain riddled with ancient rock layers, underground water channels, and seismic vulnerabilities. The core structure is being stabilized using an interlocking tripod foundation, essentially 3 massive reinforced concrete legs that descend deep into bedrock and distribute loads across varying geological strata. This level of engineering finesse, executed in such tight urban quarters, would be nearly impossible to approve or coordinate in any major US city. The United States, once the pioneer of vertical construction, now lags far behind in realizing anything this sophisticated. While America still debates the merits of transit-oriented development and smart cities, Chongqing is actively embedding multi-use superstructures into the heart of its downtown. The Trade and Commerce Center will integrate luxury residences, commercial office spaces, high-end retail, and a world-class observation deck, all woven together with intelligent infrastructure and high-speed vertical transport systems. Elevators in this building will reach speeds exceeding 10 meters per second, operating with dynamic AI-assisted routing that reduces congestion and balances loads in real time. There is no equivalent system functioning at this scale in the US. In terms of construction methodology, Chinese crews are using a hybrid steel-concrete core that's pre-assembled off-site and lifted into place using climbing cranes that ascend the structure as it grows. Every element is meticulously pre-engineered with millimeter tolerances, and components are delivered just in time via dedicated supply corridors supported by smart logistics hubs. Compare this to the US, where even mid-rise towers in major cities often suffer from months-long delays due to material backlogs or labor shortages. China isn't improvising. China is executing with a military-like discipline and an engineering precision that the American construction industry hasn't mustered since the 1960s. Once the Chongqing International Trade and Commerce Center reaches full operational status in 2027, it will serve not just as a commercial anchor, but as a vertical city unto itself. A tower that absorbs the pressure of urban density, solves logistical challenges vertically, and embodies the sheer willpower of a country intent on mastering its terrain. In contrast, the US continues to repurpose office towers from the Cold War era and debate whether it can modernize without tearing itself apart politically. Meanwhile, China is quietly rewriting the playbook and building monuments like this one, while the rest of the world watches, stunned and left behind.
The construction of the East Side Access Project in New York City is one of the most complex and technically challenging transit undertakings in the history of the United States. Designed to connect the Long Island Railroad to a new terminal beneath Grand Central Terminal in Manhattan, this massive infrastructure project required the excavation of multiple tunnel systems, the construction of subterranean caverns, and the integration of entirely new rail systems within one of the most densely built environments in the world. Spanning decades of planning and construction, the project unfolded deep beneath the city's surface, demanding extraordinary precision and coordination across multiple engineering disciplines. At the core of the East Side Access Project was the tunneling phase, which involved the excavation of nearly 15 miles of new tunnels beneath Queens and Manhattan. This began with the deployment of tunnel boring machines, each weighing hundreds of tons and extending over 400 feet in length. These machines were launched from access points in Queens and advanced westward under the East River through soft ground and bedrock. To maintain stability in varying geological conditions, different TBM technologies were employed, including earth pressure balance and slurry shield methods. The TBMs simultaneously excavated and installed precast concrete segmental liners, forming a continuous circular tunnel as they progressed. Each tunnel required continuous monitoring of ground movement, with real-time data collected from instruments embedded in the surrounding soil and rock. Ground stabilization techniques such as ground freezing and jet grouting were employed where necessary to prevent subsidence and protect adjacent infrastructure. Spoil material from the excavation was transported via conveyor belts and muck trains to designated removal sites, where it was processed and disposed of according to environmental regulations. Once the primary tunnels were completed, work shifted to the construction of the Manhattan Caverns, which would house the new terminal platforms and tracks. Located approximately 100 feet below street level, these caverns were excavated using the controlled drill and blast method. Each blast was carefully calculated to fracture rock without damaging existing subway lines and utilities above. The excavated spaces were then stabilized using rock bolts, shotcrete, and steel ribs, followed by waterproofing membranes and reinforced concrete linings. The new terminal complex beneath Grand Central was designed as a bi-level structure featuring 4 platforms and 8 tracks. The layout included numerous cross passages, ventilation shafts, and emergency egress corridors. Each level was constructed with reinforced concrete floor slabs supported by massive girders and columns, engineered to distribute loads uniformly across the cavern walls and foundations. Structural steel framing was used extensively in mezzanine and concourse areas to allow for open spaces and flexibility in architectural finishes. A major component of the East Side Access Project was the installation of a complex track and signal system. This involved laying continuously welded rail on concrete ties set in ballastless track beds, designed for durability and low maintenance. The track alignment required precision to meet curvature and grade requirements, particularly as the trains transitioned from tunnel approaches into the terminal. Overhead catenary systems were replaced by a third rail electrification system compatible with Long Island Railroad rolling stock, necessitating the integration of new power substations and switching equipment. Advanced signal and train control systems were installed, including communications-based train control to enhance capacity and safety. These systems required extensive cabling, signal houses, and testing to ensure interoperability with the existing rail network. Fiber optic communication networks were also laid throughout the tunnels and terminal areas to support operational control and real-time monitoring. Vertical transportation was another critical aspect, given the significant depth of the terminal. High-capacity escalators, some extending over 90 feet in length, were installed to move passengers efficiently between the mezzanine and platform levels. Additionally, multiple banks of high-speed elevators were constructed to provide accessibility and redundancy. Mechanical rooms housing air handling units, chillers, and backup power systems were strategically located throughout the terminal to support passenger comfort and operational resilience. In Queens, the Harold Interlocking, one of the busiest rail junctions in the country, had to be completely reconfigured to accommodate new track alignments for East Side access. This required the installation of new flyovers, viaducts, and switches, while maintaining uninterrupted train service for Amtrak and the Long Island Railroad. Work in this area was conducted in multiple phases, involving track outages scheduled years in advance and executed with military precision. New signal towers and interlockings were built to streamline train movements and improve operational flexibility. The construction of the new Highmark Stadium in Orchard Park, New York, the future home of the Buffalo Bills, involves the development of a modern open-air sports facility designed to enhance fan experience, operational efficiency, and long-term durability in a region known for its severe winter conditions. This multi-year, multi-billion-dollar project is being built adjacent to the existing stadium, allowing uninterrupted use of the current facility during construction. The project requires extensive coordination of site development, structural engineering, vertical construction, mechanical systems, and logistics in order to deliver a stadium suited for National Football League operations and year-round community use. The site work began with extensive geotechnical surveys and soil borings to determine subsurface conditions. Given the clayey soils and shallow groundwater common in the region, the stadium's foundation system was designed to include deep foundations consisting primarily of driven steel piles and reinforced concrete drilled piers. These foundation elements extend to layers of dense till or weathered bedrock to ensure settlement control and resistance to frost heave, a key concern in the region's freeze-thaw cycles. Foundation work also included pile caps and grade beams, which tied together vertical loads from superstructure columns and distributed them into the subgrade. Following earthwork and foundation construction, the stadium's structural system began rising from the ground. The primary vertical and lateral force-resisting systems are composed of structural steel frames using wide flange beams, box columns, and truss members to accommodate large spans over seating bowls and concourse levels. Erection of steel components was carried out using crawler cranes, mobile tower cranes, and temporary bracing towers to stabilize elements until permanent connections were completed. Bolted connections predominated for speed and ease of assembly, with some welded joints required for moment-resisting frames in the main concourse and canopy structures. The stadium features a continuous seating bowl with multiple tiers, supported by cast-in-place concrete raker beams and precast concrete treads and risers. These structural components were manufactured off-site and trucked in for installation, using heavy-duty lifting equipment. Precast elements were aligned and shimmed into place, then grouted and anchored to ensure a rigid connection to the supporting steel or concrete framework. Vomitories, stairs, and circulation corridors were integrated into the bowl structure, incorporating slip-resistant coatings and embedded tactile strips for accessibility compliance. A prominent feature of the stadium is its canopy structure, which is designed to cover a significant portion of the spectator seating while remaining open at the field level. The canopy is supported by long-span cantilevered trusses projecting from the outer edge of the upper seating bowl. These trusses were fabricated in segments and lifted into position, then post-tensioned to reduce deflection and improve load transfer. The canopy cladding includes metal panel systems and translucent roofing materials to allow natural light penetration while providing shelter from rain and snow. Snow load considerations were a primary design constraint, requiring robust framing and drainage systems to prevent ice accumulation and structural overstress. Mechanical systems within the stadium include air handling units, hydronic heating systems, and ventilation equipment tailored to the open-air nature of the venue. Large mechanical rooms were installed beneath the seating bowl and in service cores, housing boilers, pumps, and fan systems. Given the region's cold climate, radiant heating systems were embedded into portions of the concourses and key field-level areas to prevent freezing and ensure operational continuity. The field itself incorporates a subgrade heating system to prevent turf freezing and ensure safe playing conditions during late season and playoff games. Electrical systems included high-capacity feeders, switchgear, and lighting panels distributed through electrical closets and conduits hidden within wall cavities and floor trenches. LED lighting systems were installed throughout the stadium, including field lighting, which was mounted on the canopy structure to provide even illumination with minimal glare. Emergency power systems, including diesel generators and battery-backed UPS systems, ensure continuity of life safety and broadcast operations during outages. The stadium's vertical circulation is supported by escalators, elevators, and wide staircases, designed to handle rapid ingress and egress of over 60,000 spectators. Vertical cores were constructed using reinforced concrete shear walls with embedded elevator guide rails and MEP chaseways. All passenger elevators were installed with regenerative drives and machine roomless technology to reduce energy use and maintenance demands. Within the stadium envelope, premium seating areas, suites, clubs, and press facilities were constructed using structural framing and high-end interior finishes. These spaces included raised access floors, custom millwork, acoustic ceiling systems, and advanced audiovisual integration for real-time data display and broadcast capabilities. Extensive mechanical zoning and separate air handling units were used to isolate VIP areas from general circulation zones. On the exterior, the stadium design incorporates architectural metal panels, stone veneer, and curtain wall glazing in key entry points. Exterior plazas and arrival zones were constructed with reinforced concrete pavement, pavers, and landscape features, including stormwater planters and snow melt systems embedded in walkways. Security measures such as bollards, surveillance systems, and controlled entry points were coordinated with structural and civil design. Logistics played a central role throughout the construction process. Given the tight construction schedule, materials were procured using just-in-time delivery methods with on-site laydown areas minimized through advanced planning. Winter construction required temporary enclosures, heated work areas, and cold weather concrete practices, including admixtures and thermal blankets. The Bay City Green Hydrogen Plant is an advanced industrial facility designed to produce hydrogen using electrolysis powered by renewable energy sources, primarily solar and wind. Situated in proximity to both energy supply corridors and industrial hydrogen demand centers, the project begins with extensive land development, which includes grading, drainage design, and geotechnical stabilization to support heavy equipment loads and ensure safe operation under varying environmental conditions. Electrical grounding systems are embedded in the foundational layout to protect sensitive electrolysis components from surges and lightning. Once the site is cleared and compacted, construction of the primary electrolysis units begins. These systems, typically using proton exchange membrane or alkaline electrolyzer stacks, require a precise mechanical and electrical assembly environment. Prefabricated skid-mounted modules are delivered to the site, each containing electrolyzer cells, transformers, rectifiers, and water purification units. These modules are set on reinforced concrete pads with embedded anchor bolts to withstand thermal cycling and mechanical vibrations. Deionized water feed systems are installed, incorporating reverse osmosis and filtration units to ensure electrolyte purity, which is critical for electrolyzer efficiency and longevity. Adjacent to the electrolyzers, a high-voltage substation is constructed to interface with renewable energy sources. This substation steps down incoming electricity from transmission voltages to operational levels suitable for the direct current systems feeding the electrolysis stacks. Power distribution infrastructure includes underground cable trays, switchgear enclosures, and load centers with automated fault detection. Battery energy storage systems are often co-located to buffer intermittent generation from renewables, smoothing out power supply fluctuations to maintain consistent hydrogen output. Hydrogen produced on-site is directed through stainless steel piping systems to compression units where it is pressurized for storage or distribution. These compressors are housed within sound-attenuated enclosures to meet regulatory noise limits and are equipped with redundant safety valves and blowdown stacks. Storage vessels, typically cylindrical tanks rated for several hundred bar, are constructed using high-strength carbon steel alloys and are fitted with pressure and temperature monitoring instrumentation. A control center oversees plant operations via a distributed control system that integrates sensors, flow meters, and programmable logic controllers. Real-time data acquisition enables operators to optimize electrolysis efficiency and respond to any anomalies. The plant also incorporates emergency shutdown systems, gas leak detection, and fire suppression equipment to meet industrial safety standards. Upon completion, commissioning involves a phased startup of each system, pressure testing of gas lines, calibration of instrumentation, and validation of control logic before the plant is cleared for continuous green hydrogen production. Rebuilding from near-total devastation, the reconstruction of Tyndall Air Force Base following the impact of Hurricane Michael in 2018 required a complete reimagining of military infrastructure in the face of extreme climate events. The project began with an intensive demolition and debris removal phase, where thousands of tons of structural wreckage, downed trees, and contaminated materials were cleared using heavy equipment including hydraulic excavators, high-reach loaders, and roll-off trucks. Before any vertical construction resumed, environmental remediation teams had to address storm-related hazardous material spills and groundwater contamination risks. Once the site was stabilized, the reconstruction effort shifted toward creating a base of the future, grounded in resilience, energy efficiency, and smart infrastructure. One of the foundational strategies was the implementation of mission-driven zoning, in which facilities were grouped by operational function: flight line, support, administrative, residential, allowing for optimized utility distribution, vehicular movement, and force protection measures. Civil engineers realigned roadways, constructed new perimeter security systems, and raised the elevation of key buildings to avoid future storm surge damage. The new construction used tilt-up concrete panels and hurricane-rated curtain wall systems across most structures. Load-bearing walls were designed to resist sustained winds exceeding 180 miles per hour, and all roofs were anchored with enhanced uplift connectors and continuous load paths to transfer forces to the foundation. Building envelopes included closed-cell spray foam insulation and thermally broken aluminum fenestration systems to improve energy performance while maintaining blast resistance in mission-critical zones. A major focus of the reconstruction was integrating advanced electrical microgrid systems. Redundant power generation sources, including solar PV arrays, diesel generators, and battery storage, were installed to ensure operational continuity during grid outages. Subsurface duct banks were rerouted and reinforced to improve storm resilience, and switchgear facilities were elevated above base flood elevation to avoid future water intrusion. Hangar complexes for F-35 aircraft required particularly high-precision construction tolerances. These steel-framed structures incorporated massive rolling hangar doors, anti-static flooring systems, and integrated fire suppression systems specifically engineered for jet fuel hazards. Mechanical systems included custom air handling units with high filtration capabilities to protect both personnel and aircraft maintenance environments. Drainage was redesigned with sustainability and resiliency in mind. Bioswales, reinforced outfalls, and permeable pavements were incorporated to improve stormwater quality and reduce erosion. Stormwater retention basins were expanded and linked to smart monitoring systems that automatically adjust outflows based on weather forecasts and rainfall events. The reconstruction also deployed extensive building automation systems across administrative and housing facilities. Lighting, HVAC, and security systems are now centrally controlled and monitored, allowing real-time energy optimization and system diagnostics. Residential zones were rebuilt to meet LEED Silver and above standards, using impact-resistant windows, high-efficiency HVAC units, and low-flow plumbing fixtures.
Bringing TSMC Fab 21 to life in North Phoenix demanded one of the most technically advanced semiconductor facility builds in the United States. This megaproject required a fusion of high-precision cleanroom construction, utility-heavy support infrastructure, and robust seismic and environmental engineering solutions, all executed on a tight timeline within a desert environment. The development began with mass grading across hundreds of acres to establish a stable platform for both the fab itself and the sprawling central utility building, administration spaces, and logistics hubs. Earth-moving operations required both over-excavation and recompaction to meet rigorous load-bearing criteria, particularly for the cleanroom slab, which must maintain a virtually zero tolerance for differential settlement. Vibration mitigation began at the soil level. where layered sub-base configurations and damping materials were installed to reduce micro-vibrations that could interfere with nanometer-scale lithography. Foundation work incorporated a network of heavily reinforced mat slabs and pile caps. In certain zones, deep foundations were installed using auger cast piles to transfer loads well below any compressible strata. The main fab structure was built using steel moment frames and composite metal deck slabs, designed to support not only the clean room above, but also extensive overhead mechanical and process utilities routed through a heavily loaded interstitial floor. Clean room construction demanded extreme precision. Raised access flooring allowed for laminar airflow, while walls and ceilings were clad in non-shedding, chemically resistant materials. Every seam, panel joint, and utility penetration was sealed to ISO standards, with HEPA filter housings integrated into a grid of fan filter units in the ceiling plenum. Environmental conditions, temperature, humidity, and airborne particle count had to remain within ultra-narrow tolerances, requiring redundant HVAC systems, deionized water production units, and high-efficiency gas scrubbers. The scale of process utility integration was immense. An underground pipe rack corridor was constructed to distribute ultra-pure water, specialty process gases, slurry lines, vacuum systems, and chemical waste returns. All pipe systems were color-coded and installed with leak detection, double containment, and purge capability. Above-ground utility bridges spanned between the central utility plant and the fab, carrying high-volume, chilled water, nitrogen, and clean dry air lines across multiple levels. The central utility building itself was a complex of power transformers, chillers, boilers, air compressors, and chemical delivery systems. Redundant backup generators and uninterruptible power supplies were installed to ensure zero downtime in critical process areas. High-voltage electrical rooms were isolated with arc flash rated enclosures, while transformers and switchgear were mounted on isolated slabs to prevent mechanical vibration transmission. Environmental compliance drove the inclusion of advanced waste treatment facilities and air emissions controls. Scrubber stacks, flare systems, and liquid neutralization tanks operated around the clock to process both hazardous and non-hazardous waste streams. Permitting required continuous environmental monitoring and real-time reporting capabilities. Security and access control were embedded into the site design. Guardhouses, secure perimeters, and biometric access zones were installed to protect intellectual property and personnel. The internal circulation of materials followed a just-in-time logistics model, supported by automated guided vehicles and robotic systems operating in designated corridors beneath the cleanroom floor. In the case of China's Chengdu Greenland Tower, scheduled for completion in 2026, the message it sends to the United States is deafening. We build faster, taller, and smarter, and we do it in cities most Americans still haven't heard of. While US skylines remain largely frozen in time, dominated by 20th century icons like the Willis Tower or the Empire State Building, China's second-tier cities are launching futuristic super-tall skyscrapers with the kind of complexity and ambition that the US construction sector hasn't touched in decades. The Chengdu Greenland Tower is not just a tall building, it's an ultra-modern engineering challenge wrapped in a sculptural form that responds to seismic threats, urban density, and environmental sustainability, all while reaching above 460 meters in height. Located in a high-risk earthquake zone in Sichuan province, the structure is being built with a tuned mass damper system and a composite megaframe core, incorporating cutting-edge materials like high-performance steel and triple-layered laminated glass. This is not ornamental architecture. It's a hyper-optimized vertical system engineered to stand firm through major seismic events while hosting thousands of workers and residents. American builders have not produced anything this complex in the last 2 decades. Efforts to construct super talls in US cities are routinely bogged down in zoning disputes, FAA height restrictions, or budget collapses. Meanwhile, Chengdu, once dismissed as a regional backwater, is executing a vertical city that blends high-rise office, residential, and hotel functions into a single integrated tower. And it is doing so with logistical precision and architectural finesse. Foundation works required deep pile caissons sunk through clay-heavy soil layers, stabilized by an intricate diaphragm wall system. The engineering firms behind the tower developed site-specific simulations to predict seismic behavior and tailored the structural core to shift torsion loads away from high occupancy areas. Elevator systems inside the Chengdu Greenland Tower will include some of the fastest double-deck lifts ever installed in China. Traveling at speeds American skyscraper designers haven't dared to implement outside theoretical models. Vertical transportation planning has been handled with millisecond optimization, reducing wait times and energy usage through machine learning algorithms tied into the building management system. This is not just design, it's architecture embedded with computation and real-time control, something the US has only lightly experimented with in prototype buildings. China's capacity to realize this level of structural and systems integration in a city like Chengdu, not even one of its three largest metropolises, reveals just how far the engineering gap has grown. The Chengdu Greenland Tower, once it opens in 2026, will stand as a vertical demonstration of China's lead in megastructure execution. While the US continues to debate climate adaptation, seismic safety, and urban densification, China is putting all three into practice, stacked floor by floor into the clouds. It's a stark and undeniable contrast. One nation is constructing the future skyline, while the other is still managing the legacy of a past era.
The construction of One Vanderbilt, a super tall skyscraper located adjacent to Grand Central Terminal in Midtown Manhattan, involved a highly complex sequence of engineering, structural, and logistical operations. Rising to a height of over 1,000 feet, One Vanderbilt integrates advanced construction techniques and urban transit improvements into a single vertical development, setting a new benchmark for commercial office towers in densely built environments. The project demanded meticulous planning and coordination, particularly given its proximity to historic structures, active transit infrastructure, and high pedestrian traffic zones. Site preparation began with the demolition of several pre-existing mid-rise buildings. This process involved asbestos abatement, structural dismantling, and foundation removal. Due to the tight urban footprint and adjacent properties, much of the demolition was carried out using high-reach excavators and hydraulic breakers rather than traditional implosion or large-scale mechanical demolition. Once the site was cleared, excavation commenced for the new foundations, which reached over 60 feet below grade to accommodate the tower's deep basement levels and the integration of a new transit hall connecting to Grand Central Terminal. Subsurface conditions required the use of slurry wall construction to provide lateral earth support during excavation. A perimeter slurry wall, composed of reinforced concrete panels formed within bentonite-supported trenches, was installed to retain surrounding soils and water. Tiebacks and internal bracing were employed to ensure wall stability as excavation advanced. Excavated material was removed using conveyor belts and dump trucks, with loads scheduled during off-peak hours to minimize traffic disruption. The foundation system consisted of a combination of spread footings and deep caissons drilled into bedrock. The caissons, some exceeding 6 feet in diameter, were constructed using large rotary drilling rigs and reinforced with steel cages before being filled with high-strength concrete. These elements were designed to transfer the enormous vertical loads from the tower into the Manhattan schist below. A thick matte foundation slab was poured over the caissons, utilizing thousands of cubic yards of concrete delivered in a continuous 24-hour operation. The superstructure of One Vanderbilt utilized a composite structural system combining a reinforced concrete core with structural steel framing. The core, which houses elevators, stairs, and mechanical risers, was constructed first using slip-form technology. This technique involved the continuous pouring of concrete into a moving formwork system. allowing rapid vertical advancement. The core served as the backbone of the building, providing torsional resistance and lateral stability. Around the core, structural steel beams and columns were erected to form the building's floor framing. High-strength bolted and welded connections linked the steel elements, while metal decking and concrete topping slabs formed the composite floor systems. The building's tapering profile and multiple setbacks required specially fabricated steel members and custom connection details. Each steel floor was erected using tower cranes positioned within the core, later climbed to upper levels as the building rose. To achieve the building's slender profile and withstand wind loads, One Vanderbilt incorporated tuned mass damping systems at its upper levels. These systems consist of massive weights suspended and supported by hydraulic or spring systems, which counteract building sway during high wind events. The structural engineers also designed a system of outrigger trusses and belt trusses that tied perimeter columns to the central core, distributing lateral forces more efficiently and enhancing overall rigidity. The curtain wall system featured unitized glass and aluminum panels that were pre-assembled and tested off-site for quality and performance. Each panel included insulated glazing units with solar control coatings, contributing to the building's energy efficiency. The panels were hoisted into place using monorail rigs and suction equipment mounted to floor slabs, with careful alignment to ensure thermal and air barrier continuity. Integrated ventilation louvers and operable windows provided occupant comfort and facilitated natural airflow. Mechanical systems for One Vanderbilt were designed for high performance and tenant flexibility. The building was served by multiple mechanical floors housing chillers, air handling units, and water pumps. The chilled water system used high-efficiency centrifugal chillers with variable frequency drives, connected to fan-powered terminal units distributed throughout tenant spaces. The vertical distribution of mechanical services was handled through stacked mechanical shafts integrated within the core. Electrical infrastructure included redundant feeders from the utility grid, emergency diesel generators, and automatic transfer switches to ensure uninterrupted service. Advanced building management systems controlled lighting, HVAC, and security systems with sensors deployed to monitor occupancy and optimize energy use. High-capacity risers for telecommunications, data, and security cabling were installed to accommodate diverse tenant requirements. Vertical transportation consisted of over 40 elevators divided into zoned banks, some of which utilized destination dispatch technology to minimize wait times and energy use. Express elevators connected lower floors to sky lobbies, while service elevators were designed with extra depth to handle large tenant equipment and furniture. At the base of the tower, a new transit concourse was constructed to improve access to Grand Central Terminal and the subway lines beneath it. This involved underpinning sections of the historic terminal structure and constructing new passages, escalators, and ticketing areas. Complex waterproofing systems, including bentonite mats and integral water stops, were installed to protect the subterranean spaces from groundwater intrusion. Public realm improvements included widened sidewalks, landscape plazas, and an open-air pedestrian corridor that created visual and physical connections to Grand Central Terminal. Paving, lighting, and street furniture were coordinated to enhance pedestrian circulation and safety. Rising prominently over the Corpus Christi ship channel, the Harbor Bridge Replacement Project represents a transformative upgrade to the region's transportation and maritime infrastructure. The effort to construct the new bridge begins with significant preparatory work, including clearing, grading, and establishing access roads for heavy machinery. Crews undertake extensive geotechnical surveys to design deep foundation systems that can safely support the towering cable-stayed structure in a coastal environment prone to high winds, corrosive salt air, and variable soil conditions. The core of the construction involves the installation of massive drilled shaft foundations. These are created using rotary rigs that bore deep into the substrata, often through layers of clay, sand, and limestone. Reinforcing steel cages are then lowered into the shafts and encased in concrete to form durable vertical supports. Given the location over navigable waters, temporary work platforms and marine barges are mobilized to provide access and material staging for overwater operations. The centerpiece of the bridge consists of two towering pylons that anchor the cable-stayed design. These pylons are constructed incrementally using a climbing formwork system that allows each concrete lift to cure before the next section is poured. Precision alignment is essential as the pylons must remain perfectly vertical over hundreds of feet of elevation. Once the pylons reach their full height, installation of the stay cables begins. These high-tension steel cables are anchored at the pylons and radiate outward in a fan-like array to support precast bridge deck segments. Deck segments are installed using a balanced cantilever method, where sections are added symmetrically from both sides of the pylon to maintain structural equilibrium. Each segment is carefully aligned and post-tensioned into place, forming the long-span roadway over the ship channel. Throughout this process, real-time structural health monitoring systems are employed to measure stress, displacement, and vibration to ensure safety and integrity during construction. The bridge approaches are constructed concurrently, involving the erection of elevated spans supported by precast concrete girders and pier caps. These components are assembled using cranes and falsework, followed by placement of the riding surface and expansion joints. The project also includes roadway realignments, upgraded interchanges, and the integration of pedestrian and bike paths to enhance multimodal accessibility. Upon completion, extensive commissioning activities verify all structural, electrical, and drainage systems. The new harbor bridge will provide significantly improved clearance for maritime traffic, greater traffic capacity for vehicles, and enhanced resilience against hurricanes and seismic events, marking a new chapter in regional infrastructure advancement. Beneath the surface of Biscayne Bay, the Port of Miami Tunnel represents one of the most complex underwater infrastructure undertakings in the southeastern United States. Constructed to alleviate downtown Miami's chronic congestion caused by thousands of daily truck trips to and from the port, this project required advanced tunneling methods, massive marine coordination, and exacting safety systems. The overall plan was to connect the MacArthur Causeway directly to Port Miami via twin tunnels, each approximately 3/4 of a mile in length, buried beneath the seabed and designed to handle bidirectional vehicular traffic. Before tunneling could begin, preparatory works focused on dredging and stabilizing the soft bay soils. Extensive geotechnical investigations were conducted using boreholes and cone penetration tests to classify the variable limestone and sand strata that would be encountered. Ground improvement methods such as jet grouting and ground freezing were considered in preliminary phases, but the design ultimately relied on a pressurized face tunnel boring machine capable of navigating both soft ground and denser rock formations. Custom built in Germany and shipped in segments, the TBM used on this project was over 40 feet in diameter and weighed several hundred tons. Assembly took place in a large launching pit on Watson Island, where reinforced concrete diaphragm walls and a trimmy-placed base slab formed the structural cradle. The boring process progressed incrementally, with the TBM advancing just a few feet per hour, while simultaneously installing precast concrete segment rings behind it to form the tunnel lining. These segments, fabricated off-site and transported to the launch area, were equipped with waterproof gaskets and dowel interlocks to ensure tight seals under hydrostatic pressure. The tunnel alignment passed beneath the shipping channel, which introduced unique challenges related to buoyancy, water ingress, and structural reinforcement. At the deepest sections, the tunnel crown lay more than 100 feet below the water surface. To resist both groundwater pressure and seismic loading, the tunnel lining thickness and steel reinforcement were increased, especially at the crown and invert where stress concentrations were highest. Real-time instrumentation inside the TBM provided feedback on ground conditions, face pressure, and segment placement accuracy, helping to mitigate risks of sinkholes or blowouts. Simultaneously, surface-level works included the construction of ventilation buildings at each portal. These reinforced concrete structures house massive axial fans, emergency backup power systems, and life safety controls. Each tunnel is equipped with a full suite of fire suppression systems, including deluge sprinklers and fire-rated wall finishes. A network of electronic signage, CCTV, and incident detection sensors runs the entire tunnel length, all connected to a centralized control room staffed continuously. Upon completion of tunneling, crews moved on to road deck construction, lighting installation, and system commissioning. Pavement was laid using specialized low-sag asphalt mixes designed to withstand constant vehicle loading in a confined environment. Final testing included simulated fire events, emergency evacuation drills, and full-scale load testing to ensure operational readiness.
From the outset, the Mack Innovation Park in Scottsdale presented a high-performance build scenario shaped by advanced logistics, rapid vertical development, and site-specific architectural programming. Situated within a high-demand commercial corridor, the project required precision scheduling and a phased construction approach to erect multiple speculative and build-to-suit structures tailored for high-tech manufacturing, office, and research uses. The first major activity involved grading and compaction over a multi-acre footprint. Scottsdale's desert soil conditions demanded moisture conditioning, followed by repeated passes of sheepsfoot and smooth drum rollers, monitored continuously with nuclear density testing to confirm subgrade integrity. Stormwater retention and drainage systems were integrated early, using a combination of underground retention vaults and surface bioswales lined with riprap to mitigate flash flood risks typical of monsoon seasons. Civil crews trenched for extensive underground utilities, embedding large diameter conduits and reinforced concrete storm drains well before foundations were poured. Structural systems across the park consisted primarily of tilt-up concrete panels, a method selected for its speed, cost efficiency, and thermal mass benefits in a desert climate. Once formwork was set on large slab beds, each wall panel was cast with embedded window bucks, utility sleeves, and conduit stubs. Steel reinforcement was tied with exacting placement to meet seismic and wind load criteria. After curing, these panels were lifted using high-capacity hydraulic cranes and braced temporarily with diagonal steel supports until the roof structure was completed. The concrete mix design included admixtures for shrinkage control and compressive strength exceeding 5,000 pounds per square inch to allow for early panel lifting without compromising durability. Roof structures utilized open web steel joists supported by steel girders and columns anchored to footings with precision-aligned base plates and epoxy grouted anchor bolts. Decking was installed using high shear connectors and puddle welds, then covered with insulation and a reflective TPO membrane for energy efficiency. HVAC systems were rooftop mounted and supported by custom-built steel dunnage frames to reduce structural penetration through the roof. Mechanical coordination involved extensive pre-planning through building information modeling to avoid clashes between ductwork, piping, and electrical raceways within tight ceiling plenum spaces. Interior build-outs were varied depending on the end user, but commonly involved raised access flooring, modular cleanroom compatible partitions, electrostatic discharge safe surfaces, and filtered ventilation systems for research or manufacturing spaces. Electrical infrastructure featured heavy capacity switchgear, isolated ground panels, and redundant feeds where mission-critical operations were anticipated. Fiber optic cabling and wireless mesh networks were embedded throughout to support high data throughput and low latency connectivity. The exterior envelope included architectural elements such as aluminum curtain walls, insulated metal panels, and sunshade louvers oriented according to solar exposure analysis. Landscaping featured xeriscape planting schemes with drip irrigation systems and shaded pedestrian pathways to enhance sustainability and user comfort. Site lighting was designed with cut-off optics and smart sensors to minimize light pollution while ensuring safety. If there's one project that has completely shaken the core of American hydroengineering circles, it's China's Yarlung-Zangbo Medog hydropower project. Slated for completion in the late 2020s, this colossal undertaking is not just an energy generator, it's an audacious declaration of engineering dominance. The scale, complexity, and geopolitical audacity of damming the world's deepest canyon on the edge of the Tibetan Plateau is something the United States, with its fractured permitting systems and endless litigation cycles, simply could not imagine executing. For China, it's another step in an aggressive infrastructural vision that no other country dares to match. What makes this project particularly mind-bending is its location. The Yarlung-Zangbo River, which later becomes the Brahmaputra, snakes through some of the most remote, geologically unstable, and topographically extreme terrain on the planet. The proposed site, near Medog County, is surrounded by seismic fault lines, landslide-prone cliffs, and a canyon deeper than even the Grand Canyon in Arizona. This is not a place where one simply builds anything. Yet China is building the world's largest hydropower station by output, in defiance of every conventional engineering restraint. While the United States still celebrates the Hoover Dam, an impressive project for its time, China is constructing something that will dwarf it in every conceivable metric: installed capacity, vertical drop, construction risk, and environmental scale. American hydro projects haven't crossed the 10,000 megawatt threshold in decades, while this Chinese project is projected to deliver nearly triple that amount. It's not just a question of ambition, it's about execution. In the US, environmental impact assessments alone could stall a similar venture for over 20 years. In China, environmental management is integrated into the design, but not used as a bureaucratic weapon to halt national progress. To tunnel through the Himalayan bedrock, Chinese engineers are deploying some of the world's largest tunnel boring machines ever built, capable of grinding through high-pressure metamorphic rock under extreme tectonic stress. These machines operate in tandem, digging multiple access shafts and flood diversion channels in parallel, supported by an army of geotechnical specialists monitoring every vibration and pressure fluctuation in real time. Concrete pouring is staged by altitude, requiring aerial logistics chains using heavy lift helicopters and drone-supported cable cars. Workforce camps and supply depots were built years in advance, anticipating weather patterns and monsoon cycles that would paralyze most other nations' efforts. The dam structure itself, still under assembly, is expected to be a multi-arch double curvature design, one that balances seismic resistance with the massive force of Himalayan meltwater. High-strength, roller-compacted concrete and hybrid fiber reinforcement technologies are being used, many of which haven't even been adopted at scale in the United States. American firms still struggle to retrofit bridges with seismic dampers. China is building an entire megastructure atop an active fault zone and making it earthquake resilient from the foundation up. When the Yarlung-Zangbo hydropower project goes online later this decade, it won't just be a symbol of energy independence or regional integration. It will be a direct engineering rebuttal to the stagnation of American infrastructure. China is taking on the hardest, most dangerous, and most technically challenging projects in the world, and finishing them. Meanwhile, the US continues to patch potholes and argue over environmental permitting for high-speed rail that may never arrive. The message could not be clearer. Sometimes a single structure can say more about a nation's priorities and capabilities than any policy speech or infrastructure bill.
The construction of Hudson Yards, located on the west side of Manhattan, represents one of the most ambitious private real estate developments in the history of the United States. The site, once dominated by an active train yard known as the West Side Yard, posed a formidable engineering challenge due to the need to build over 20 rail tracks in constant operation. The project's realization required a complex orchestration of civil, structural, and mechanical systems in order to create a functional and stable platform that could support multiple high-rise structures while allowing uninterrupted train service beneath. The initial phase of construction centered around the creation of a massive platform, which involved installing approximately 300 caissons. These deep foundation elements, bored between existing rail lines and into the bedrock below, served as vertical supports for the deck that would eventually span the yard. Each caisson was constructed using a combination of drilled shafts reinforced with steel and filled with high-strength concrete, reaching depths of up to 100 feet. Due to the spatial constraints imposed by the active rail operations, each caisson had to be installed with extreme precision using specialized rigs positioned during coordinated windows when train traffic was paused or rerouted. Above the caissons, structural steel grillages and transfer girders were installed to distribute building loads across the uneven geometry of the train yard. These steel elements, many of which weighed in excess of 100 tons, were fabricated off-site and delivered during low-traffic hours to reduce disruptions. Erection of the steel frame platform was carried out using crawler cranes and gantry systems designed to maneuver around the tight constraints of the site. Temporary scaffolding, shoring towers, and falsework were used extensively to stabilize the platform sections during assembly. Once the platform structure was complete, a complex network of utility corridors, ventilation systems, and access points was integrated into the void space between the train tracks and the platform deck. This included active cooling systems designed to dissipate the heat generated by diesel locomotives, as well as fire suppression systems, emergency egress routes, and conduits for electrical and telecommunication lines. Special attention was paid to drainage and water management, as the deck needed to remain impermeable and resistant to both surface runoff and the thermal stresses caused by seasonal freeze-thaw cycles. Simultaneously, vertical construction began above the platform with the erection of high-rise towers featuring both steel and reinforced concrete superstructures. Tower cranes were mounted directly onto the platform and sometimes even cantilevered off the side to accommodate building footprints. For residential and commercial towers, high-strength concrete was pumped from staging areas outside the yard through a series of reinforced pipelines, ensuring consistent quality and flow rate. Core walls, which housed elevators, stairs, and utilities, were slip-formed in a continuous process to accelerate vertical progress and maintain alignment. Curtain wall systems consisting of glass and aluminum panels were fabricated off-site and installed using motorized hoists and mast climbers. These units were engineered to meet stringent performance criteria related to wind loads, thermal insulation, and sound attenuation due to the exposure of the site and its proximity to the Hudson River. The facade systems were also integrated with mechanical louvers and operable components to support the sustainable design targets set for the project. Mechanical, electrical, and plumbing installations were coordinated using building information modeling to avoid clashes and maximize available ceiling space. Centralized utility plants were constructed to serve multiple buildings with chilled water, steam, and power, using a combination of cogeneration and high-efficiency equipment. These plants were interconnected through a network of underground tunnels and risers, carefully designed to minimize energy loss and facilitate future maintenance access. Interior build-outs varied depending on occupancy type, but generally involved raised access floors, demountable partition systems, and state-of-the-art fire protection and life safety systems. For the retail podium, load-bearing transfer slabs were installed to accommodate large open floor plans and dynamic occupancy loads. This required the use of high-performance concrete with additives that enhanced pumpability and cured strength, particularly for spans exceeding 50 feet. Public realm elements, including the plaza and landscaping above the platform, were constructed using a layered assembly that included structural foam, drainage mats, root barriers, and engineered soil. These layers supported a diverse range of plantings, pedestrian pathways, and stormwater retention features. Custom-designed tree pits and planters were built into the deck slab, allowing mature trees to thrive despite limited soil depth and exposure to wind shear. Throughout the construction process, logistics were a primary concern, as the confined urban site required just-in-time delivery scheduling, off-site staging areas, and constant coordination with city agencies and transit authorities. Noise and vibration monitoring, environmental controls, and dust suppression systems were continuously deployed to minimize impacts on neighboring communities and infrastructure. The overall success of Hudson Yards was underpinned by an integrated project delivery model, which relied on collaboration among architects, engineers, contractors, and stakeholders from the earliest planning stages. This level of integration allowed for accelerated construction timelines, efficient risk mitigation, and optimized resource use, culminating in the completion of a new urban neighborhood that seamlessly integrates infrastructure, real estate, and public space atop an active rail yard.